The universe should not exist. And yet, here it is. Everything we see, stars, planets, people, should have been wiped out before it began. In the beginning, matter and antimatter were created together, but they destroy each other when they meet. So how did anything survive? This is one of the biggest mysteries in science. Somehow, against all odds, our universe won the coin toss. It didn't collapse into nothing. Instead, it grew, spread, and formed everything we know. So before we begin, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating journey through space. The universe exists. This simple fact, when deeply considered, presents one of the most profound and unsettling mysteries imaginable. We find ourselves living in a cosmos of immense scale and intricate complexity, a realm filled with stars, galaxies, and perhaps most astonishingly, life and conscious beings capable of pondering their own existence. Yet the overwhelming intuition, from a purely logical standpoint, is that nothing should exist at all. The state of nothingness, a complete absence of matter, energy, space, time, and even the laws that govern them, seems to many the most straightforward and fundamental possibility. Why then is there something rather than nothing? This is the big question, a riddle that stretches the limits of human comprehension and challenges the very foundations of our understanding of reality. It is not merely a philosophical musing, but a puzzle deeply embedded in the most current scientific discoveries. Science has provided a breathtaking narrative of how the universe began and evolved from a hot, dense state in the Big Bang, roughly 13.8 billion years ago. It explains the formation of stars, planets, and even the complex chemistry that led to life. But it struggles to address the underlying reason for the existence of the initial conditions or the fundamental laws that allowed such a beginning to unfold. These laws, like gravity, electromagnetism, and the nuclear forces, appear exquisitely precise. Their strengths and values seem perfectly calibrated, as if by a cosmic dial, to permit the formation of stable atoms, long-lived stars, and complex chemistry necessary for life. If, for instance, the strong nuclear force, which binds protons and neutrons together in atomic nuclei, were only slightly weaker, stable atoms beyond hydrogen would not exist, making chemistry and life impossible. Conversely, if it were slightly stronger, hydrogen would fuse too rapidly, and stars would burn out before life could begin. Consider the ratio of the electromagnetic force to the gravitational force. This ratio is an incredibly large number, approximately 10 to the power of 40. This enormous difference is critical. If gravity were much stronger relative to electromagnetism, stars would be too hot and short-lived, or they might collapse before forming. If gravity were much weaker, matter would never clump together to form stars or galaxies. The universe would be a diffuse, lifeless gas. These are not isolated examples. Numerous fundamental constants and initial conditions of the universe exhibit this astonishing fine-tuning. The mass of the electron, the expansion rate of the universe, the density of dark energy, countless parameters seem to fall within a very narrow range that permits a universe conducive to complexity and life. To many, such precise values for a universe that could potentially take on any arbitrary set of values seems incredibly improbable, almost like rolling a dice and getting the same specific number 1,000 times in a row. The very concept of the vacuum, seemingly empty space, further deepens the mystery. According to quantum physics, a true vacuum is not empty. It teems with virtual particles constantly popping into and out of existence, imbued with a vast amount of energy. Theoretical calculations for this vacuum energy predict an amount so enormous that it should have caused the universe to expand at an unimaginable rate, ripping itself apart almost instantaneously, or to collapse back on itself. Yet, observations show that the vacuum energy, identified with dark energy, is incredibly small, almost zero, a discrepancy of about 120 orders of magnitude between theory and observation. This is arguably the largest mismatch between theory and experiment in all of science. If the vacuum energy were as large as predicted, no stable structures, no stars, no galaxies, no life could ever form. The fact that it is so tiny is another profound puzzle contributing to the question of why anything exists. Another perplexing aspect is the asymmetry between matter and antimatter. In the early universe, energy could convert into particle-antiparticle pairs. Theory predicts that equal amounts of matter and antimatter should have been created. However, if this were the case, as the universe cooled, matter and antimatter would have annihilated each other, leaving behind a cosmos filled only with radiation, devoid of any particles that could form stars, planets, or us. Yet, our universe is overwhelmingly composed of matter. This minuscule excess of matter over antimatter, roughly one particle for every billion particle-antiparticle pairs, is the reason everything we see exists. The precise mechanisms that led to this tiny imbalance remain one of the great unsolved problems in particle physics. Without this 1 in a billion anomaly, the universe would still be effectively nothing in terms of observable structure. The question of why something exists rather than nothing transcends the simple "how did it start" question. Even if we could trace the universe back to an ultimate single point or a pre-existing state, we would still be left with the question, why that point? Why those pre-existing conditions? Why those laws of physics? Is there an ultimate fundamental reason for these things to be the way they are, or are they simply brute facts? Things that just are, without further explanation. The scientific method excels at describing how processes occur within a given set of rules and initial conditions, but it is not equipped to explain why those rules and conditions exist in the first place, or why there is a universe to apply them to. This profound challenge lies at the very heart of physics, cosmology, and philosophy, inviting us to confront the limits of our empirical knowledge and perhaps the very nature of reality itself. The concept of nothingness might seem straightforward at first glance, simply the absence of everything. However, upon closer examination, it quickly devolves into a surprisingly complex and elusive idea, posing significant challenges to both philosophers and physicists. When we ask why something exists rather than nothing, a crucial first step is to precisely define what nothing truly means. Is it an empty box? But a box implies space, and space is something. Is it empty space? But space itself is a component of our universe, a fabric that can stretch and warp. If we remove space, then where is this nothing? Philosophically, absolute nothingness would entail the absence of everything. No matter, no energy, no space, no time, no physical laws, no consciousness, no dimensions, no properties, and even no potential for anything to exist. It is not merely a vacuum or an empty container. It is the absence of the container itself. Imagining such a state is incredibly difficult, perhaps impossible for minds accustomed to existing within a framework of space and time. Even when we try to conceive of it, we often inadvertently project some form of background or conceptual space onto our mental image. This difficulty in conception itself suggests that nothingness might be an unstable or even contradictory state. In physics, nothing has a very different meaning from this absolute philosophical void, and this distinction is crucial for understanding the universe's origin. When physicists speak of the vacuum or empty space, they are referring to the lowest possible energy state of quantum fields. This is far from nothing. A quantum vacuum is a bustling arena of activity, governed by the laws of quantum mechanics. Virtual particles, briefly existing pairs of matter and antimatter, constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This phenomenon is not hypothetical. It has measurable effects, such as the Casimir effect, where two uncharged metal plates placed very close together experience a small attractive force due to differences in the vacuum energy between them and outside them. Thus, even the emptiest region of space is a sea of fluctuating energy and potential. This nothing of physics is, in fact, a very rich something. The Big Bang Theory describes the evolution of the universe from an extremely hot, dense state, but it does not, in its standard form, explain what caused that initial state or what existed before it. Some theories propose a singularity, a point of infinite density and temperature from which the universe expanded. Other models, like inflationary cosmology, suggest the universe emerged from a tiny quantum fluctuation within a pre-existing false vacuum, a state of extremely high energy density that eventually decayed, releasing the energy that formed our universe. Even in these scenarios, the universe doesn't arise from absolute nothingness. It arises from a pre-existing quantum field, albeit one that is in a very unusual and unstable state. The question then shifts. Why did this false vacuum exist? Why did it possess the properties it did? The very existence of physical laws further complicates the idea of a universe arising from absolute nothing. If nothing means truly nothing, then there would be no laws of physics, no principles of logic, and no underlying mathematical structures to govern any potential emergence. Yet, the universe operates according to incredibly precise and consistent laws. Where did these laws come from? Did they exist before the universe, somehow allowing it to come into being? If so, then they themselves are something, an abstract but potent reality, implying that even the purest form of nothingness is never truly absolute. This suggests a deep interplay between existence and the rules that govern it. Some philosophical arguments suggest that nothingness is inherently unstable. If there is truly nothing, then there are no constraints, no reasons, and no forces to prevent something from coming into being. In a state of absolute lack, perhaps there is no barrier to the emergence of possibility. This is a subtle argument, as it implies that potentiality itself is a form of something. If a possibility can arise, then the framework for possibility must exist, which again is not absolute nothing. Other perspectives suggest that something is the default state, and nothing is an abstract construct that we struggle to define because it defies our experienced reality. We are beings that exist, in a universe that exists, operating under laws that exist. Our fundamental experience is one of presence, not absence. The challenge of creation ex nihilo, creation from nothing, is profound. If something truly came from nothing, it would violate one of the most fundamental principles of physics, the conservation of energy and mass. Energy and mass cannot be created or destroyed, only transformed. For the entire universe, with all its vast energy and matter, to simply appear from an absolute void would seem to break this bedrock principle. While quantum fluctuations allow for temporary borrowing of energy, this is always within a pre-existing energy framework. The jump from true nothing to something remains an intellectual leap that physics currently cannot fully explain, leading back to the original profound mystery. Why is there a universe at all, when the ultimate nothing appears to be the logical default? This continuous struggle to define and imagine absolute nothingness underscores just how peculiar and improbable the existence of our universe truly is. The universe, as we know it, began with an event of unimaginable energy and density, widely known as the Big Bang. This theory is the leading scientific model describing the evolution of our cosmos, from its earliest moments to its current vastness. It is important to clarify that the Big Bang is not an explosion in pre-existing space, but rather the rapid expansion of space itself. Current scientific understanding allows us to trace the universe's history back to an astonishingly early point, though the precise instant of creation, often referred to as a singularity, remains an area of active research and theoretical challenge. Our journey begins at a time unimaginably close to the very beginning, perhaps at 10 to the power of minus 43 seconds after the initial spark, a period known as the Planck epoch. At this epoch, the universe was incredibly small, perhaps no larger than a tiny speck, and unimaginably hot, with temperatures reaching over 100 million degrees Celsius, or 10 to the power of 32 Kelvin. All four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are believed to have been unified into a single super force. Our current laws of physics, including Einstein's general theory of relativity and quantum mechanics, break down at this extreme scale, preventing us from describing what precisely happened at or before this moment. Following the Planck epoch, the universe underwent a period of extraordinarily rapid expansion called cosmic inflation. Following the Planck epoch, the universe underwent a period of extraordinarily rapid expansion called cosmic inflation, which occurred between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang. During inflation, the universe expanded exponentially, growing by a factor of at least 10 to the power of 26 in an incredibly brief instant. This rapid stretching smoothed out any irregularities, explaining why the universe appears so uniform on large scales, the horizon problem, and why its geometry is flat, the flatness problem. Inflation also stretched quantum fluctuations to cosmic scales, planting the seeds for the large-scale structures, galaxies and galaxy clusters, we observe today. At the end of inflation, the enormous energy driving this expansion converted into a hot, dense soup of fundamental particles, marking the reheating of the universe. As the universe continued to expand and cool, different forces began to separate from the unified superforce. Quarks and leptons, the fundamental building blocks of matter, formed from the raw energy. For a fleeting moment, roughly 10 to the power of minus 12 seconds after the beginning, the universe was a dense hot plasma of quarks, gluons and leptons, including electrons and neutrinos. As the temperature continued to drop, around 1/1,000,000th of a second after the start, quarks began to bind together to form protons and neutrons, the building blocks of atomic nuclei. This process was driven by the strong nuclear force. For every billion antiquarks, there was approximately one more quark, creating a tiny but crucial imbalance that led to the matter-dominated universe we see today, rather than a cosmos filled only with radiation. Over the next few minutes, as the universe cooled to temperatures around 1 billion degrees Celsius, Big Bang nucleosynthesis began. Protons and neutrons jostling in the expanding plasma started to fuse together under immense pressure and heat, forming the nuclei of light elements. Primarily hydrogen nuclei, single protons, combined to form deuterium, which then fused into helium nuclei, 2 protons and 2 neutrons. Small amounts of lithium were also formed. This period lasted only for about the first 20 minutes of the universe's existence. The precise ratios of hydrogen, helium and lithium observed throughout the universe today, roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium, provide one of the strongest pieces of evidence supporting the Big Bang theory. For the next approximately 380,000 years, the universe remained a hot, opaque plasma. Electrons were still free, constantly scattering photons, light particles, preventing light from travelling far without being absorbed or deflected. The universe was effectively foggy. As expansion continued, the universe cooled to around 3,000 degrees Celsius. At this temperature, electrons were finally able to combine with the light nuclei, protons and helium nuclei, to form stable, neutral atoms, primarily hydrogen and helium. This event is known as recombination. With electrons now bound in atoms, photons were free to travel unimpeded through space. These ancient photons, stretched and cooled by billions of years of cosmic expansion, are what we detect today as the cosmic microwave background, CMB radiation. The CMB is a faint glow of microwave light coming from all directions in space, providing a direct baby picture of the early universe. Its remarkable uniformity, with tiny temperature fluctuations, further supports the inflationary model and the Big Bang. Following the release of the CMB, the universe entered a period known as the Dark Ages, lasting for hundreds of millions of years. During this time, there were no stars or galaxies, and the universe was filled with neutral hydrogen and helium gas. Gravity, acting on the tiny density fluctuations imprinted during inflation, slowly began to pull together regions of slightly denser gas. These denser clumps gradually grew, collapsing under their own gravity. After about 400 million years to 800 million years, the first stars ignited within these collapsing gas clouds, marking the end of the Dark Ages and the beginning of the era of rionization, as their intense ultraviolet radiation stripped electrons from neutral hydrogen atoms again. These first stars were massive and short-lived, forging heavier elements like carbon oxygen and iron through nuclear fusion within their cores. When these massive stars exploded as supernovas, they scattered these newly formed elements throughout the cosmos, providing the raw materials for subsequent generations of stars, planets, and eventually life. From these humble beginnings, the universe has continued to expand, cool, and evolve. Over billions of years, gravity sculpted the expanding matter into the complex structures we observe today. Galaxies containing billions of stars, arranged into vast galaxy clusters and superclusters, forming a cosmic web. The ongoing expansion of the universe, first observed by Edwin Hubble in the 1920s, where distant galaxies are moving away from us at speeds proportional to their distance, is a direct consequence of the Big Bang. The Big Bang theory, supported by a wealth of observational evidence including the cosmic microwave background, the precise abundance of light elements, the observed expansion of the universe, and the distribution of large-scale cosmic structures, provides a coherent and compelling narrative of how our universe came to be and how it has developed over its immense history. It describes the how, even as the why remains an enduring enigma. The existence of our universe, teeming with stars, galaxies, and life, presents a profound puzzle when one considers the underlying physical laws and constants that govern it. It is as if the cosmos operates according to a perfect recipe, where numerous fundamental ingredients, the strengths of forces, the masses of particles, the initial expansion rate, are set to values that appear astonishingly precise, allowing for the emergence of complexity and consciousness. This observation is known as cosmic fine-tuning, and it is not a philosophical assertion but a conclusion drawn from detailed scientific analysis of the universe's properties. The probability of all these parameters aligning by random chance to permit a life-supporting universe seems incredibly remote, akin to winning a lottery where the odds are 1 in many, many billions of billions. Consider the initial expansion rate of the universe following the Big Bang. If the universe had expanded even slightly faster, matter would have dispersed too quickly, preventing gravity from pulling together gas and dust to form stars and galaxies. The cosmos would have remained a dilute, featureless gas. Conversely, if the expansion rate had been infinitesimally slower, gravity would have quickly overwhelmed the outward momentum, causing the universe to collapse back in on itself long before stars or planets could form. The observed rate of expansion is balanced on a razor's edge, allowing for billions of years of cosmic evolution, sufficient time for stars to form, live, and produce the heavier elements necessary for planets and life. This delicate balance is one of the most striking examples of fine-tuning. Another critical parameter is the density of the universe, specifically its total energy density. This determines the overall geometry of space. If the density were too high, the universe would be closed, eventually collapsing. If it were too low, the universe would be open, expanding forever and becoming increasingly empty. Our universe appears to be remarkably flat, meaning its density is very close to a critical value that allows it to expand indefinitely, while still permitting the formation of large-scale structures. The likelihood of the universe having precisely this critical density at the earliest moments, given the vast range of possibilities, is exceedingly small. This flatness problem is one of the reasons the theory of cosmic inflation was proposed, suggesting an early period of exponential expansion that smoothed out the universe and drove its density towards this critical value. However, inflation itself requires specific initial conditions to occur. The cosmological constant, which represents the energy density of empty space and is responsible for the accelerating expansion of the universe, presents perhaps the most extreme example of fine-tuning. Theoretical predictions for its value, based on quantum field theory, are vastly larger than what is observed, by a factor of approximately 120 orders of magnitude. If the cosmological constant were even slightly larger than its observed tiny value, the repulsive force it exerts would have caused the universe to expand so rapidly that matter could never have clumped together to form galaxies, stars, or any stable structures. The universe would have been a desolate, rapidly expanding void. If it were significantly negative, it would have caused an immediate collapse. The fact that its value is so incredibly small, yet positive, allowing for both structure formation and accelerated expansion, is a profound mystery. The fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, also exhibit extraordinary fine-tuning. Their relative strengths are crucial. For instance, the ratio of the electromagnetic force to gravity is immense, about 10 to the power of 40. If this ratio were significantly different, the universe would be fundamentally altered. If electromagnetism were much weaker relative to gravity, stars would be too hot and short-lived, or they might not be able to form at all. If gravity were much stronger, stars would burn out too quickly, and the universe would be dominated by black holes. The precise balance allows for stars that live for billions of years, providing stable energy sources for planets. The masses of fundamental particles such as electrons and protons are equally critical. The ratio of the electron mass to the proton mass affects the size and properties of atoms and molecules. If electrons were much heavier, atoms would be much smaller, and chemical reactions would proceed differently, potentially preventing the complex chemistry necessary for life. If electrons were much lighter, they might not be able to form stable orbits around nuclei. The precise mass difference between a proton and a neutron is also vital. A neutron is slightly heavier than a proton. If the neutron were even slightly lighter, all protons would have converted into neutrons in the early universe, leading to a universe with no hydrogen, and thus no water or long-lived stars. If the neutron were significantly heavier, it would have decayed too quickly, preventing the formation of helium and other light elements during Big Bang nuclear synthesis. Beyond the fundamental constants, the specific energy levels within atomic nuclei are also finely tuned. A famous example is the Hoyle resonance in carbon. Carbon, with 6 protons, is the backbone of all known life. It is formed in stars when 3 helium nuclei fuse together. This fusion process is extremely improbable unless there is a specific energy level, or resonance, in the carbon nucleus that precisely matches the energy of the fusing helium nuclei. Sir Fred Hoyle predicted this resonance before it was experimentally confirmed, arguing that its existence was necessary for carbon to be produced in sufficient quantities for life. Similarly, the energy level of oxygen is also critical, allowing it to form from carbon and helium, but preventing all carbon from being converted into oxygen. These precise nuclear resonances are essential for the cosmic abundance of the elements that make up our bodies and our planet. The initial conditions of the universe also play a crucial role. The universe began with incredibly low entropy, meaning it was in a highly ordered state. This initial order allowed for the subsequent increase in entropy, driving processes like star formation, planet formation, and the development of life. If the universe had started in a high entropy disordered state, it would have quickly reached a state of thermal equilibrium, preventing any complex structures from forming. The source of this initial low entropy is another deep puzzle within the fine-tuning argument. All these examples, from the expansion rate to particle masses and nuclear resonances, point to a universe that seems remarkably, almost impossibly, suited for existence and complexity. Gravity, one of the 4 fundamental forces of nature, is the architect of the cosmos on the grander scales. Though it is by far the weakest of the 4 forces, its unique properties, being long-range and always attractive, make it the dominant force in shaping the universe, from the formation of stars and planets to the vast structures of galaxies and galaxy clusters. Unlike the nuclear forces, which act only over incredibly short distances, gravity's influence extends infinitely, diminishing with distance but never truly disappearing. In Albert Einstein's revolutionary theory of general relativity, gravity is not described as a force pulling objects together, but rather as a curvature of space-time itself, caused by the presence of mass and energy. Objects simply follow the curves in this fabric, giving the appearance of attraction. In the very early universe, immediately following the Big Bang and the period of cosmic inflation, gravity played a pivotal role. While inflation smoothed out the universe to a remarkable degree, it also stretched tiny quantum fluctuations into macroscopic density variations. These minuscule differences in the distribution of matter and energy, amplified by inflation, became the seeds from which all large-scale structures would eventually grow. gravity's relentless pull began to act on these slightly denser regions. Over hundreds of millions of years, these regions slowly accumulated more and more matter, drawing in surrounding gas and dust. This process, driven solely by gravity, led to the formation of the first stars, then galaxies, and eventually the vast cosmic web of interconnected galaxy clusters that spans the observable universe. Without gravity, or if its strength were even slightly different, this process would not have unfolded as it did. The formation of stars is a direct consequence of gravity's grip. Within vast clouds of gas and dust known as nebulae, gravity causes denser pockets to begin to collapse inward. As these pockets contract, the material within them becomes increasingly compressed and heated. This collapsing region, known as a protostar, continues to shrink under its own gravity. The temperature and pressure in its core steadily rise until they reach a critical point, millions of degrees Celsius and immense pressures, where nuclear fusion can ignite. At this point, hydrogen atoms in the core begin to fuse into helium, releasing enormous amounts of energy. This outward pressure from fusion balances the inward pull of gravity, creating a stable star that can shine for millions or billions of years. If gravity were too weak, these gas clouds would never collapse sufficiently to ignite fusion, and no stars would form. If gravity were too strong, stars would collapse too rapidly, burning out quickly or forming black holes without ever reaching a stable, long-lived phase. Gravity is also the architect of galaxies. After the first stars formed, gravity continued to pull them together, along with remaining gas and dark matter into larger structures. These collections of billions of stars, gas, dust, and dark matter are what we call galaxies. Our own Milky Way galaxy, a spiral of hundreds of billions of stars, is held together by gravity. The stars orbit the galactic center, influenced by the combined gravitational pull of all the matter within the galaxy, including the mysterious dark matter, which provides the necessary gravitational scaffolding to prevent galaxies from flying apart. Galaxies themselves are not isolated. They are gravitationally bound into groups, clusters, and superclusters, forming the largest known structures in the universe. The cosmic web, a vast network of filaments and voids, is the result of gravity acting on matter over billions of years, pulling it into dense knots and leaving vast empty regions. On smaller scales, gravity governs the formation and stability of planetary systems. Around young stars, leftover gas and dust form a rotating disk. Within this protoplanetary disk, gravity causes particles to clump together, gradually forming planetesimals, which then collide and merge to build planets. Once formed, planets are held in stable orbits around their host stars by gravity. The Earth orbits the Sun, and the Moon orbits the Earth, all due to the precise balance between their orbital velocity and the gravitational pull of the larger body. This gravitational stability is crucial for maintaining conditions suitable for life over geological timescales, preventing planets from spiraling into their stars or being flung out into the cold emptiness of interstellar space. The precise strength of gravity, encoded in the gravitational constant, is incredibly fine-tuned for a universe that supports life. If gravity were even slightly stronger, its increased pull would have profound consequences. Stars would form smaller and burn hotter and faster, exhausting their nuclear fuel in a fraction of the time, perhaps only millions of years instead of billions. This would not allow enough time for complex life to evolve on any orbiting planets. Stronger gravity would also lead to more frequent and rapid formation of black holes, potentially making large regions of the universe inhospitable. Planetary orbits would be less stable, and many planets might be pulled into their stars or collide with each other. Conversely, if gravity was slightly weaker, its effects would be equally catastrophic for life. Gas clouds in the early universe might never have collapsed sufficiently to form stars. If stars did form, they would be much larger and more diffuse, with insufficient core temperatures and pressures to ignite nuclear fusion. Without fusion, stars would not shine, and no heavier elements beyond hydrogen and helium would be produced. Consequently, there would be no carbon, oxygen, nitrogen, or iron. The fundamental building blocks of planets and life, galaxies, might not coalesce, leaving the universe as a thinly dispersed gas. The precise strength of gravity ensures that stars can form, live for billions of years, and produce the elements necessary for life, while also allowing for stable planetary orbits and the formation of the large-scale cosmic structures. Its subtle yet pervasive grip is fundamental to the universe's ability to host complexity. The strong nuclear force, often simply called the strong force, is the most powerful of the four fundamental forces of nature. Its immense strength, however, is confined to an incredibly short range, acting only over distances roughly the size of an atomic nucleus, approximately 10 to the power of -15 meters. Beyond this minuscule distance, its influence diminishes so rapidly that it becomes negligible. This unique characteristic is precisely what makes it indispensable for the existence of stable matter and, consequently, for life itself. Without the strong force, the universe would be an entirely different and utterly lifeless place. The primary role of the strong force is to bind together the fundamental particles called quarks to form protons and neutrons, which are collectively known as nucleons. Quarks, which are never observed in isolation, are held together by particles called gluons, which are the carriers of the strong force. This binding is so powerful that it creates a phenomenon known as confinement, meaning quarks are permanently trapped within protons and neutrons. If one attempts to pull quarks apart, the force between them actually increases, making it impossible to isolate a single quark. This is why we only observe protons and neutrons, not individual quarks. Beyond binding quarks within nucleons, the strong force has another crucial function. It binds protons and neutrons together to form the nuclei of atoms. This is where its immense strength truly becomes apparent. Protons, being positively charged, naturally repel each other due to the electromagnetic force. This repulsion is powerful, especially within the tiny confines of an atomic nucleus. The strong force, despite its short range, is approximately 100 times stronger than the electromagnetic repulsion at nuclear distances. It is this overwhelming strength that allows protons and neutrons to stick together, forming stable atomic nuclei. Without the strong force, the electromagnetic repulsion would cause any nucleus containing more than one proton to immediately fly apart, meaning only hydrogen, with its single proton nucleus, could exist. The implications of this are profound. In the first few minutes after the Big Bang, during a period called Big Bang nuclear synthesis, the strong force was responsible for the formation of the first light atomic nuclei. As the universe cooled, protons and neutrons began to fuse. The strong force allowed a proton and a neutron to combine to form deuterium, an isotope of hydrogen. Deuterium then fused with other protons and neutrons to form helium nuclei and trace amounts of lithium. This process was extremely sensitive to the strength of the strong force. If it were even slightly weaker, protons and neutrons would not have been able to bind effectively, and the early universe would have remained a plasma of free protons and neutrons, with no heavier elements like helium forming. The strong force also governs nuclear fusion within stars, the process that powers them and creates all the heavier elements in the universe. In the cores of stars, immense temperatures and pressures force atomic nuclei close enough for the strong force to overcome their electromagnetic repulsion and fuse together. This fusion process, starting with hydrogen fusing into helium, and then helium fusing into carbon, oxygen, and all elements up to iron in more massive stars, is entirely dependent on the strong force. When stars exhaust their nuclear fuel and explode as supernovas, they scatter these newly forged elements into space, providing the raw materials for subsequent generations of stars, planets, and ultimately life. Without the strong force, no elements heavier than hydrogen could exist, and thus no chemistry, no planets, and no life. The precise strength of the strong force is another remarkable example of cosmic fine-tuning. If the strong force were even slightly weaker, by just a few percent, atomic nuclei would be unstable. Protons and neutrons would not hold together, or would do so only very tenuously. This would mean that elements like carbon, oxygen, and nitrogen, which are absolutely essential for life, could not form. The periodic table would effectively end at hydrogen. Stars would not be able to sustain fusion reactions, as the nuclei would not bind strongly enough to release energy. The universe would be a uniform, lifeless soup of hydrogen. Conversely, if the strong force were slightly stronger, again by just a few percent, it would have equally catastrophic consequences. Protons might bind too readily, perhaps even forming stable diprotons, two protons bound together, or other exotic nuclei that would prevent the formation of stable hydrogen. This would mean that hydrogen, the most abundant element in the universe and crucial for water and long-lived stars, would be unstable or quickly consumed. Furthermore, a stronger strong force might lead to all neutrons decaying into protons, or vice versa, resulting in a universe composed of only one type of nucleon. It could also make the formation of heavier elements too efficient, causing stars to burn through their fuel too quickly, or making it difficult for supernovas to disperse the elements they create. The delicate balance of the strong force ensures the stability of atomic nuclei, the existence of a diverse periodic table of elements, and the long-term energy production of stars, all prerequisites for a universe capable of supporting complex structures and life. The weak nuclear force, often simply referred to as the weak force, is one of the four fundamental interactions that govern the universe. While it is significantly weaker than the strong nuclear force and the electromagnetic force, and its range is incredibly short, acting only over distances smaller than an atomic nucleus, approximately 10 to the power of -18 meters, its role is absolutely crucial for the existence of the elements, the stability of stars, and ultimately for life itself. Unlike the strong force, which binds quarks together and holds atomic nuclei intact, the weak force is responsible for mediating processes where fundamental particles change their identity. It is the force behind radioactive decay, a phenomenon that might seem destructive but is in fact a vital cosmic sculptor. The primary mechanism through which the weak force operates is the transformation of one type of quark into another, or one type of lepton into another. Quarks are the building blocks of protons and neutrons, while leptons include particles like electrons and neutrinos. This particle transformation is mediated by messenger particles called W and Z bosons. For instance, in a common form of radioactive decay known as beta- decay, a neutron, which is composed of one up quark and two down quarks, transforms into a proton, composed of two up quarks and one down quark. This transformation involves one of the neutron's down quarks changing into an up quark, a process facilitated by the weak force. During this transformation, the neutron emits a W- boson, which then quickly decays into an electron and an antineutrino. This process changes the identity of the atomic nucleus. The neutron becomes a proton, increasing the atomic number by 1 and thus changing the element. For example, a carbon-14 nucleus with 6 protons and 8 neutrons undergoes beta- decay to become a nitrogen-14 nucleus with 7 protons and 7 neutrons. Another form is beta plus decay, where a proton transforms into a neutron, emitting a W plus boson, which then decays into a positron, the antimatter equivalent of an electron, and a neutrino. This process occurs in proton-rich nuclei and decreases the atomic number. Electron capture is a related process where an atomic nucleus captures one of its own electrons, converting a proton into a neutron and emitting a neutrino. All these transformations, mediated by the weak force, are fundamental to the stability and transmutation of elements throughout the cosmos. The weak force played an absolutely critical role in the very early universe, during the period of Big Bang nucleosynthesis, which occurred in the first few minutes after the Big Bang. At this time, the universe was a hot, dense soup of protons and neutrons. The weak force was responsible for establishing the crucial balance between the number of protons and neutrons. Initially, when the universe was extremely hot, protons and neutrons could interconvert freely through weak interactions. As the universe cooled, these interconversions became less frequent. Because neutrons are slightly more massive than protons, free neutrons tend to decay into protons via beta- decay. The weaker force dictated the rate of this decay. By the time the universe was about 1 second old, and the temperature had dropped sufficiently, the weak interactions effectively froze out. At this point, for every 1 neutron, there were approximately 7 protons. This specific proton-to-neutron ratio was absolutely vital. If the weak force had been significantly stronger, neutrons would have decayed into protons much more rapidly. This would have resulted in an even higher proton-to-neutron ratio, meaning very few neutrons would have been available to combine with protons to form helium. The universe would have been almost entirely hydrogen, with very little helium. Conversely, if the weak force had been significantly weaker, neutrons would have decayed much more slowly, leading to a higher proportion of neutrons. This would have resulted in a universe with too much helium and not enough hydrogen. The observed abundance of hydrogen, roughly 75%, and helium, roughly 25% in the universe, which is one of the key pieces of evidence for the Big Bang, is a direct consequence of the precise strength of the weak force. Without this fine-tuned strength, the elemental composition of the universe would be drastically different, preventing the formation of water, complex molecules, and ultimately, life. Beyond the early universe, the weak force continues its vital work within stars, particularly in the process of nuclear fusion that powers them. In stars like our Sun, the primary energy generation mechanism is the proton-proton chain reaction, where hydrogen nuclei fuse to form helium. The very first step of this chain involves two protons combining. For this to happen, one of the protons must transform into a neutron. This transformation, a beta plus decay, is mediated by the weak force. This particular step is incredibly slow due to the inherent weakness of the force. It is this slowness that acts as a bottleneck in the fusion process, allowing stars like the Sun to burn steadily for billions of years, providing a stable energy source over geological timescales. If the weak force were stronger, this reaction would proceed much faster, causing stars to burn through their fuel in a fraction of the time, perhaps only millions of years. This would not allow sufficient time for planets to form and for complex life to evolve. If the weak force were weaker, the reaction might be too slow to sustain stellar fusion, or it might not ignite at all, leaving the universe without shining stars. The weak force also plays a critical role in the spectacular deaths of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity. During this catastrophic collapse, electrons are forced into protons, transforming them into neutrons. This process, known as electron capture, is mediated by the weak force. The core rapidly becomes a super-dense neutron star. The sudden formation of a vast number of neutrons releases a tremendous burst of neutrinos, which are particles that interact only via the weak force. These neutrinos carry away a significant amount of energy and are believed to play a crucial role in driving the supernova shockwave that rips apart the outer layers of the star, expelling the heavy elements forged in its core out into interstellar space. Without the weak force, this mechanism would not occur, and the heavy elements necessary for planets and life would remain locked within the stellar remnants, never to become available for new solar systems. Thus, the weak force, despite its name and short reach, is an indispensable component of the cosmic recipe, enabling the precise elemental abundances and stellar lifetimes that make our universe a place where life can exist. Electromagnetism is one of the four fundamental forces of nature, and it is the force that governs all interactions between electrically charged particles. Unlike the strong and weak nuclear forces, which operate only over subatomic distances, electromagnetism has an infinite range, much like gravity. However, its effects on large scales are often masked because positive and negative charges tend to cancel each other out. Despite this, electromagnetism is the force responsible for light, electricity, magnetism, and crucially, all of chemistry and the structure of everyday matter. Without its precise strength and characteristics, the universe as we know it, with its atoms, molecules, and complex structures would simply not exist. At its most fundamental level, electromagnetism describes the attraction between particles with opposite charges and the repulsion between particles with like charges. The most familiar examples are the attraction between a negatively charged electron and a positively charged proton. This attractive force is what binds electrons to atomic nuclei, forming atoms. The electrons orbit the nucleus in specific energy levels or shells, and the electromagnetic force dictates the size and stability of these orbits. The number of electrons and their arrangement in these shells determine an atom's chemical properties. If the electromagnetic force were significantly stronger, electrons would be pulled much closer to the nucleus, making atoms incredibly tiny. This would drastically alter the way atoms interact, potentially preventing the formation of complex molecular structures. If the force was significantly weaker, electrons might not be bound to nuclei at all, or they would orbit at much larger distances, making atoms unstable or too diffuse to form stable bonds. The precise strength of electromagnetism ensures that atoms are the right size and stability to engage in the intricate dance of chemistry. Beyond individual atoms, electromagnetism is the architect of all molecules. Chemical bonds, whether ionic, covalent, or metallic, are fundamentally electromagnetic interactions between the electrons of different atoms. For example, in a covalent bond, atoms share electrons, while in an ionic bond, one atom transfers an electron to another, creating oppositely charged ions that attract each other. These bonds allow atoms to combine into the vast array of molecules that make up everything from water and carbon dioxide to complex proteins and deoxyribonucleic acid. All chemical reactions, the very essence of life processes, are governed by the electromagnetic force. The stability of liquids and solids, the properties of materials like their melting points, boiling points, and conductivity, are all direct consequences of the strength and nature of electromagnetic interactions between atoms and molecules. Without this force, there would be no chemistry, no complex structures, and no life. Electromagnetism is also the force behind light and all forms of electromagnetic radiation, including radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. These are all oscillations in electric and magnetic fields that propagate through space at the speed of light. Light is emitted when charged particles, such as electrons, change their energy levels within an atom or when they accelerate. The absorption of light also involves electromagnetic interactions, where photons transfer energy to electrons, causing them to jump to higher energy levels. This continuous exchange of electromagnetic radiation is how stars shine, how energy is transferred across vast cosmic distances, and how we perceive the universe through our eyes and instruments. The very existence of a transparent universe, where light can travel for billions of years to reach us, depends on electrons being bound in neutral atoms, which is an electromagnetic phenomenon. The balance of electromagnetism with the other fundamental forces is incredibly fine-tuned. Its strength relative to the strong nuclear force is crucial. While the strong force overcomes the electromagnetic repulsion between protons within the nucleus, electromagnetism dictates the behavior of electrons outside the nucleus. This allows for stable, diverse atomic structures. If electromagnetism were much stronger relative to the strong force, the repulsion between protons would be too great for stable nuclei to form, preventing the existence of any elements heavier than hydrogen. If it were too weak, electrons might not form stable orbits, or atoms might behave very differently. Perhaps even more striking is the balance between electromagnetism and gravity. The electromagnetic force is vastly stronger than gravity, approximately 10 to the power of 40 times stronger. This enormous difference is essential. If electromagnetism were much weaker relative to gravity, gravity would dominate at atomic scales. Atoms might collapse, or matter might clump together so densely that it would prevent the formation of the complex, open structures necessary for chemistry and biology. Conversely, if electromagnetism were even more dominant, its repulsive forces between like charges might prevent matter from clumping together to form stars and galaxies, or it might make the universe too diffuse for any large structures to coalesce. The precise ratio allows gravity to dominate on cosmic scales, forming stars and galaxies, while electromagnetism dominates on atomic and molecular scales, allowing for the intricate chemistry that underpins life. This delicate interplay ensures that the universe has both large-scale structure and fine-grained complexity, making it a perfect recipe for existence. One of the most profound and persistent mysteries in cosmology and particle physics is the puzzle of matter-antimatter asymmetry. According to our best theories, the early universe should have contained equal amounts of matter and antimatter. Yet, the universe we observe today is overwhelmingly composed of matter, with very little antimatter. This imbalance is not a minor detail. It is the fundamental reason why anything exists at all in terms of stars, galaxies, planets, and life. If matter and antimatter had been created in truly equal quantities, they would have completely annihilated each other as the universe cooled, leaving behind a cosmos filled only with radiation, a vast sea of photons devoid of any particles to form structures. To understand this mystery, we must first grasp the concept of antimatter. For almost every fundamental particle, there exists an antiparticle. An antiparticle has the same mass as its corresponding particle, but opposite electric charge and other quantum numbers. For example, the antiparticle of an electron, which has a negative charge, is the positron, which has a positive charge. The antiparticle of a proton is an antiproton, and so on. The defining characteristic of antimatter is that when a particle encounters its antiparticle, they annihilate each other, converting their entire mass into pure energy, typically in the form of gamma-ray photons. This process is incredibly efficient, as described by Albert Einstein's famous equation E=mc². In the extremely hot and dense conditions of the very early universe, immediately after the Big Bang, energy was so abundant that it could spontaneously convert into particle-antiparticle pairs. This process is a fundamental aspect of quantum field theory. For every particle created, an antiparticle should also have been created. This is a consequence of fundamental symmetries in physics, particularly the CPT symmetry, which states that the laws of physics should be the same if particles are swapped with antiparticles, charge conjugation C, if spatial coordinates are inverted, parity P, and if time is reversed, time reversal T. If particles and antiparticles were truly symmetric in their creation and behaviour, then an equal number of each should have formed. As the universe expanded and cooled, the conditions for creating new particle-antiparticle pairs eventually ceased. At this point, the vast numbers of matter and antimatter particles that had been created would have begun to annihilate each other. If there had been an exact balance, this annihilation would have been complete, leaving only a universe of light. However, our universe is clearly not just light. It is filled with galaxies, stars, and planets, all made of matter. This means that somehow, in the very early moments of the universe, there must have been a tiny, almost imperceptible excess of matter over antimatter. This excess was incredibly small. For every billion particle-antiparticle pairs that annihilated, approximately one extra matter particle survived. It is this minuscule residue, this 1 in a billion asymmetry, that constitutes all the matter we observe today. The question then becomes, what caused this tiny imbalance? This process is known as baryogenesis, referring to the creation of an excess of baryons, protons and neutrons, over antibaryons. A similar process, leptogenesis, might have created an excess of leptons, like electrons. In 1967, the Soviet physicist Andrei Sakharov proposed 3 essential conditions that must be met for baryogenesis to occur. First, there must be baryon number violation. This means that processes must exist that can change the total number of baryons. If baryon number were strictly conserved, then if you start with 0 baryons, as in a universe of pure energy, you could never end up with a net positive number of baryons. This condition implies that protons and neutrons, which are baryons, can be created or destroyed, not just transformed. Second, there must be C and CP violation. C symmetry, charge conjugation, means that the laws of physics should be the same if all particles are replaced by their antiparticles. CP symmetry combines this with P symmetry, parity or mirror reflection. If these symmetries were perfectly upheld, matter and antimatter would behave identically, and there would be no way to preferentially create more of one than the other. However, experiments have shown that both C and CP symmetries are violated in the weak nuclear force. While the observed amount of CP violation in the weak force is too small to account for the observed matter-antimatter asymmetry, it demonstrates that such violations are possible in nature, suggesting that a larger source of CP violation might exist at higher energies. Third, there must be a departure from thermal equilibrium. If the universe were always in perfect thermal equilibrium, any processes creating an asymmetry would be precisely balanced by inverse processes destroying it. Therefore, the universe must have undergone a period where it was out of equilibrium, allowing for a net production of matter. This condition is naturally met in the expanding and cooling early universe. While Sakharov's conditions provide a theoretical framework, the precise mechanism that generated this matter-antimatter asymmetry remains one of the most significant unsolved problems in particle physics and cosmology. Various theories have been proposed. One leading candidate is electroweak baryogenesis, which suggests that the asymmetry was generated during the electroweak phase transition, when the electromagnetic and weak forces separated. Another idea is leptogenesis, where a primordial asymmetry in leptons, like neutrinos, is created first, which then gets converted into a baryon asymmetry through other processes. Some grand unified theories, which attempt to unify the strong, weak and electromagnetic forces at extremely high energies, naturally predict baryon number violation, offering potential avenues for baryogenesis. The matter mystery is not just an academic curiosity, it is fundamental to our very existence. Without that tiny, inexplicable excess of matter over antimatter in the first moments of the universe, there would be no stars, no galaxies, no planets, and no life. The universe would be a featureless expanse of photons, a cosmic void where structure could never form. The search for the solution to this puzzle continues to drive research at the forefront of particle accelerators and cosmological observations, as understanding it is key to unlocking why our universe is filled with something rather than nothing. The universe, as we perceive it, is filled with brilliant stars, majestic galaxies, and glowing nebulae, all composed of ordinary matter that interacts with light. Yet, a vast body of evidence accumulated over decades of astronomical observations strongly indicates that this visible matter constitutes only a small fraction of the total mass and energy content of the cosmos. The dominant component of the universe's mass appears to be a mysterious, invisible substance that scientists call dark matter. This enigmatic material does not emit, absorb or reflect light or any other form of electromagnetic radiation, making it impossible to observe directly with telescopes. Its presence is inferred solely through its gravitational effects on the visible matter that we can detect. According to current cosmological models, dark matter makes up approximately 27% of the total mass and energy of the universe, dwarfing the mere 5% contributed by ordinary matter. The remaining 68% is attributed to an even more perplexing entity known as dark energy. The first compelling hints of dark matter emerged in the 1930s from the observations of Swiss astronomer Fritz Zwicky. While studying the Coma galaxy cluster, Zwicky noticed that the individual galaxies within the cluster were moving at speeds far too high to be gravitationally bound by the visible matter alone. Based on the amount of light emitted by the galaxies, their combined visible mass was insufficient to prevent the cluster from flying apart. Zwicky calculated that there must be a substantial amount of unseen, non-luminous matter, providing the additional gravitational pull needed to hold the cluster together. He termed this missing mass dunkle Materie, which translates to dark matter. His revolutionary idea was largely ignored for decades due to the limitations of observational astronomy at the time. Decades later, in the 1970s, American astronomer Vera Rubin and her colleagues provided overwhelming evidence for dark matter by studying the rotation curves of spiral galaxies. They measured the orbital speeds of stars and gas clouds at varying distances from the centres of numerous galaxies. Based on Isaac Newton's laws of gravity, one would expect stars further from the galactic centre, where most of the visible mass is concentrated, to orbit more slowly, similar to how planets further from the Sun orbit more slowly. However, Rubin's observations consistently showed that stars in the outer regions of spiral galaxies were orbiting at roughly the same speed as stars closer to the centre, or sometimes even faster. This flat rotation curve could only be explained if there was a vast invisible halo of matter, extending far beyond the visible spiral arms, providing additional gravitational pull. This unseen mass, which does not emit light, was identified as dark matter, confirming Zwicky's earlier suspicions on a galactic scale. Beyond galaxy rotation curves, several other independent lines of evidence strongly support the existence of dark matter. One powerful piece of evidence comes from gravitational lensing. Albert Einstein's theory of general relativity predicts that massive objects bend the fabric of space-time. causing light from distant objects to curve as it passes by. This phenomenon, known as gravitational lensing, allows astronomers to measure the total mass of galaxy clusters and other massive structures by observing how much they distort the light from background galaxies. These measurements consistently reveal that the total mass of galaxy clusters derived from their lensing effects is significantly greater than the mass accounted for by their visible stars, gas, and dust, indicating the presence of substantial amounts of dark matter. A particularly striking example is the Bullet Cluster, where two galaxy clusters have collided. Observations show that the bulk of the mass, dark matter, has passed straight through, separating from the hot gas, ordinary matter, which interacted and lagged behind. The gravitational lensing pattern clearly reveals the distribution of the dark matter distinct from the visible matter. Furthermore, the precise patterns of temperature fluctuations in the cosmic microwave background radiation, the faint afterglow of the Big Bang, provide strong support for a universe dominated by dark matter and dark energy. The amplitude and spacing of these peaks and troughs in the CMB power spectrum are highly sensitive to the total density of matter in the universe. Cosmological models that include dark matter accurately predict these observed patterns, whereas models based solely on ordinary matter do not. Similarly, numerical simulations of the universe's large-scale structure, the vast cosmic web of galaxies, clusters, and voids, cannot reproduce the observed distribution of galaxies without the gravitational scaffolding provided by dark matter. Ordinary matter alone, without the additional gravitational pull of dark matter, would not have clumped together quickly enough after the Big Bang to form the structures we see today. The nature of dark matter remains one of the greatest unsolved mysteries in physics. It is clear that dark matter is not ordinary baryonic matter, the protons and neutrons that make up atoms, that is simply dark. This is because the abundances of light elements, hydrogen, helium, lithium, produced during Big Bang nuclear synthesis, precisely predict the total amount of baryonic matter in the universe, and this amount is far less than the inferred dark matter content. Therefore, dark matter must be non-baryonic. Its most defining characteristic is its incredibly weak interaction with ordinary matter and light. It interacts primarily through gravity and possibly the weak nuclear force, but it does not participate in electromagnetic interactions, which is why it is invisible, or the strong nuclear force. Scientists have proposed various hypothetical particles as candidates for dark matter. The leading candidate for many decades has been weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to interact via gravity and the weak nuclear force, but not electromagnetically or strongly, making them very difficult to detect. Numerous experiments worldwide, such as the Xenon 101,000 experiments, are designed to directly detect WIMPs by looking for rare collisions between a WIMP and an atomic nucleus in ultrasensitive detectors shielded deep underground. So far, definitive evidence for WIMPs has remained elusive. Other proposed candidates include axions, very light hypothetical particles that could solve other problems in particle physics, and sterile neutrinos, which would be heavier, non-interacting versions of the known neutrinos. The ongoing search for dark matter particles is at the forefront of experimental particle physics, as a direct detection would revolutionize our understanding of the universe's fundamental composition and origin. In the vast cosmic expanse, gravity acts as the primary sculptor, pulling matter together to form stars, galaxies, and clusters. For much of the 20th century, cosmologists widely assumed that this gravitational pull would inevitably cause the universe's expansion, initiated by the Big Bang, to slow down over time, much like a ball thrown upwards eventually slows before falling back to Earth. However, a groundbreaking discovery made in 1998 shattered this long-held assumption and introduced an even more perplexing mystery. The universe's expansion is not slowing down, it is accelerating. This astonishing finding implies the existence of a mysterious, repulsive force permeating all of space, pushing galaxies apart at ever-increasing speeds. This enigmatic entity is known as dark energy, and it is currently believed to constitute approximately 68% of the universe's total mass energy content, making it the dominant component of our cosmos. The discovery of cosmic acceleration emerged from observations of distant Type Ia supernovae by two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team. Type Ia supernovae are the explosive deaths of white dwarf stars that reach a specific critical mass. Because they all explode under similar conditions, they are considered standard candles, astronomical objects that have a consistent intrinsic brightness. By comparing their apparent brightness as seen from Earth with their known intrinsic brightness, astronomers can precisely calculate their distances. If the universe's expansion were decelerating, distant supernovae would appear brighter than expected for their redshift, a measure of how much their light has been stretched by cosmic expansion, indicating their speed away from us, because they would have been closer at the time their light was emitted. However, the observations revealed the opposite. The distant Type Ia supernovae were fainter than expected. This meant they were much further away than they would be in a decelerating or even steadily expanding universe. The only logical explanation for this discrepancy was that the expansion of the universe had been accelerating over cosmic time. This acceleration could only be caused by a pervasive, repulsive force that pushes space-time apart, overpowering gravity's attractive pull on the larger scales. This mysterious force was given the name dark energy. The discovery was so significant that it earned the Nobel Prize in Physics in 2011 for the leaders of the two teams. The properties attributed to dark energy are as baffling as its existence. First, it is a repulsive force, actively pushing space apart rather than pulling matter together. This directly counteracts the effects of gravity on cosmic scales. Second, it appears to be smoothly distributed throughout space, not clumping into galaxies or clusters like matter. Third, and perhaps most perplexing, its energy density does not dilute as the universe expands. Unlike matter and radiation, whose densities decrease as the volume of the universe grows, the energy density of dark energy seems to remain constant. This constant density means that as the universe expands, dark energy becomes progressively more dominant relative to matter and radiation. In the early universe, matter and radiation dominated the expansion. However, as the universe aged and expanded, their densities diluted, allowing dark energy's influence to become significant around 5 billion to 6 billion years ago, at which point it began to drive the observed accelerated expansion. The leading theoretical candidate for dark energy is the cosmological constant, often denoted by the Greek letter lambda L. This concept was initially introduced by Albert Einstein in his equations of general relativity in 1917, as a term to achieve a static universe, which was the prevailing belief at the time. He later called it his biggest blunder after Edwin Hubble's discovery of the expanding universe. However, the cosmological constant has been resurrected as the simplest explanation for dark energy. If it is indeed a cosmological constant, it represents the intrinsic energy of empty space, an energy that does not change as space expands. This model fits current observational data remarkably well. The major challenge with the cosmological constant, however, is the vacuum problem, or cosmological constant problem. Quantum field theory predicts that the vacuum of space should possess an enormous amount of energy due to quantum fluctuations, virtual particles constantly popping into and out of existence. When these theoretical predictions are calculated, they yield a vacuum energy density that is about 120 orders of magnitude larger than the tiny value observed for dark energy. This colossal discrepancy is the largest mismatch between theory and observation in all of science, indicating a profound gap in our understanding of fundamental physics. Other theoretical possibilities for dark energy include quintessence, a hypothetical dynamic scalar field that permeates space. Unlike a cosmological constant, the energy density of quintessence could vary over time and space. This model offers more flexibility but also introduces more complexity, and requires the existence of a new fundamental field. Another alternative approach is to consider modifications to gravity itself. Perhaps Einstein's theory of general relativity, while highly successful, needs to be modified or extended on extremely large cosmic scales, and there is no need for a separate dark energy component. The accelerated expansion is simply a manifestation of gravity behaving differently. However, no compelling alternative theory of gravity has yet gained widespread acceptance. The future fate of the universe is heavily dependent on the nature of dark energy. If dark energy is indeed a cosmological constant, then the accelerated expansion will continue indefinitely. Galaxies will continue to recede from each other at ever-increasing speeds, eventually disappearing beyond our observable horizon. The universe will become increasingly cold, vast, and empty, leading to a scenario known as the Big Freeze, or heat death. In a more extreme hypothetical scenario, if dark energy were to strengthen over time, it could lead to a big rip, where its repulsive force would eventually become strong enough to tear apart galaxies, then stars and planets, and ultimately even atoms themselves. The existence and nature of dark energy remain one of the most pressing questions in modern cosmology, fundamentally influencing our understanding of the universe's ultimate destiny and why it exists in its currently expanding dynamic state. In classical physics, a vacuum is typically understood as empty space, a region completely devoid of matter and energy. However, quantum mechanics, our most successful theory describing the behavior of matter and energy at the smallest scales, paints a radically different picture. According to quantum field theory, the vacuum is far from empty. It is a teeming, effervescent sea of activity, constantly fluctuating with virtual particles spontaneously popping into and out of existence. This inherent energy of the vacuum is a direct consequence of fundamental quantum principles, particularly the Heisenberg uncertainty principle, which states that one cannot simultaneously know, with perfect precision, certain pairs of properties, such as a particle's energy and the time it possesses that energy. This principle allows for fleeting violations of energy conservation, enabling particle-antiparticle pairs to spontaneously emerge from nothing, provided they annihilate each other within a tiny fraction of a second, effectively borrowing energy from the vacuum before paying it back. These ephemeral virtual particles, along with the zero-point energy inherent in all quantum fields, even at absolute zero temperature, quantum systems possess a minimum amount of energy, contribute to an intrinsic energy density of empty space. When physicists attempt to calculate the total vacuum energy density by summing up the contributions from all known quantum fields, such as the electromagnetic field, electron fields, quark fields, and so on, the results are astonishingly large. If one applies a typical energy cutoff at the Planck scale, which is roughly 10 to the power of minus 35 meters, and represents the smallest physically meaningful distance where quantum gravity effects are expected to become significant, the calculated vacuum energy density is enormous. It predicts an energy density so vast that it should curve spacetime immensely, leading to an incredibly powerful repulsive gravitational effect. This theoretical prediction leads directly to what is known as the vacuum catastrophe, or the cosmological constant problem, which is widely regarded as the most significant quantitative discrepancy between theory and observation in all of science. Observations of the accelerating expansion of the universe attributed to dark energy suggest that the vacuum of space does indeed possess a positive energy density. However, the observed value of this dark energy is extraordinarily tiny, about 120 orders of magnitude smaller than the value predicted by quantum field theory. To put this colossal mismatch into perspective, it is like expecting to win a lottery with odds of 1 in 10 to the power of 120, and then finding that you won with just one ticket. The observed value of the vacuum energy is roughly 10 to the power of minus 9 joules per cubic meter, while theoretical predictions based on quantum fields can range from 10 to the power of 110 to 10 to the power of 119 joules per cubic meter. This profound discrepancy poses a fundamental challenge to our understanding of the universe. If the vacuum energy were as large as predicted by quantum mechanics, its repulsive gravitational effect would be so powerful that it would have caused the universe to expand at an unimaginably rapid rate from its very inception, tearing itself apart almost instantaneously. There would have been no opportunity for matter to clump together, no stars to form, no galaxies to coalesce, and certainly no life to emerge. The universe would have been a desolate, rapidly expanding void of almost nothing but diffuse radiation. The fact that the observed vacuum energy is so incredibly small, yet non-zero, allowing for cosmic structures to form and for life to exist, is one of the deepest puzzles in modern physics. The vacuum problem highlights a major incompatibility between our two most successful physical theories: quantum mechanics, which governs the microscopic world, and general relativity, which describes gravity and the large-scale structure of the universe. Quantum mechanics demands a vast energy from the vacuum, while general relativity dictates that such a vast energy would have catastrophic gravitational effects that are clearly not observed. This suggests that one or both of these theories are incomplete, or that there is a fundamental piece of physics missing that would reconcile their predictions. Many theoretical approaches have been proposed to resolve the vacuum problem, but none have yet provided a fully satisfactory solution. One idea involves supersymmetry, a hypothetical extension to the standard model of particle physics. Supersymmetry postulates that for every known particle, there exists a heavier superpartner. In a perfectly supersymmetric universe, the positive contributions to vacuum energy from bosons would exactly cancel out the negative contributions from fermions, leading to a net vacuum energy of precisely zero. However, our universe is clearly not perfectly supersymmetric, as superpartners have not been observed at their predicted masses. If supersymmetry is broken, it could still reduce the calculated vacuum energy significantly, but it typically doesn't reduce it enough to match the observed tiny value, only mitigating the problem by many orders of magnitude rather than solving it completely. Another approach appeals to the anthropic principle. This idea suggests that we observe a universe with a small vacuum energy, precisely because only such a universe can support the formation of complex structures, galaxies, stars, and ultimately conscious observers. If the vacuum energy were much larger, no such structures would form. This line of reasoning often leads to the concept of a multiverse, where our universe is just one of an immense number of universes, each with different physical constants and initial conditions, including varying vacuum energies. In this scenario, we simply happen to live in one of the rare universes where the vacuum energy is compatible with our existence. While conceptually appealing to some, the multiverse idea is not directly testable, and is viewed by others as pushing the problem outside the realm of empirical science. Other attempts to solve the vacuum problem involve hypothetical dynamical cancellation mechanisms, where some unknown physics causes the vacuum energy to dynamically relax or adjust itself to a tiny value over cosmic time. Alternatively, some theories propose modifications to gravity itself on very large scales, suggesting that Einstein's general relativity might not be the complete description of gravity in the early universe or at cosmic distances, and that the observed acceleration attributed to dark energy is a consequence of these modified gravitational laws rather than an intrinsic vacuum energy. However, these alternatives face their own theoretical challenges and have not yet provided a compelling resolution. The vacuum problem remains a stark reminder that despite our impressive scientific progress, there are profound aspects of the universe's fundamental nature that continue to elude our complete understanding, standing as a testament to the fact that the universe should not exist in its observed form, yet it does. The universe, at its most fundamental level, operates under rules that defy our everyday intuition and common sense. While classical physics, developed by figures like Isaac Newton and James Clerk Maxwell, accurately describes the motion of planets, the flight of projectiles, and the behavior of light and electricity on macroscopic scales, it utterly fails when applied to the incredibly small realm of atoms and subatomic particles. Here, a different set of principles, collectively known as quantum mechanics, takes over. This theory, developed throughout the early 20th century by brilliant minds such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, reveals a reality that is probabilistic, interconnected, and profoundly strange, challenging our very notions of what constitutes reality. One of the most astonishing aspects of quantum mechanics is the principle of superposition. In the classical world, an object has a definite state at any given moment. A coin is either heads or tails, a light switch is either on or off, a particle is in one specific location. However, in the quantum realm, a particle can exist in multiple states simultaneously. An electron, for instance, can be in a superposition of being in two different places at once, or having its spin pointing both up and down at the same time. It is not that we simply do not know its state. Rather, the particle truly exists in all these potential states concurrently until it is measured or observed. This concept is famously illustrated by the thought experiment of Schrödinger's cat, where a cat inside a sealed box is simultaneously alive and dead until the box is opened and its state is observed. This bizarre property is not just a theoretical construct, it is a fundamental aspect of how quantum systems behave and has been experimentally verified numerous times. Another cornerstone of quantum weirdness is wave-particle duality. Common sense tells us that something is either a wave, like a ripple in water or a sound wave, or a particle, like a tiny billiard ball. Light for centuries was debated as either one or the other. Quantum mechanics revealed that all quantum objects, including light and matter particles like electrons, protons, and even entire atoms, exhibit properties of both. They can behave like waves, displaying phenomena such as diffraction and interference patterns, and they can also behave like discrete particles, having a definite position and momentum. The most famous demonstration of this is the double-slit experiment. If a beam of electrons is fired at a screen with two narrow slits, and a detector screen is placed behind it, the electrons create an interference pattern, characteristic of waves, even if they are sent one by one. This suggests each electron is somehow passing through both slits simultaneously as a wave. However, if a detector is placed at the slits to observe which path each electron takes, the interference pattern disappears, and the electrons behave like classical particles, passing through only one slit. The act of observation seems to force the quantum object to choose a definite particle-like state, collapsing its wave-like superposition. Furthermore, quantum mechanics introduces the idea of quantization. Unlike classical physics, where properties like energy or angular momentum can take on any continuous value, in the quantum world many properties are quantized, meaning they can only exist in discrete specific packets, or quanta. For example, electrons in an atom can only occupy specific energy levels. They cannot exist at energies in between. When an electron moves from a higher energy level to a lower one, it emits a photon, a quantum of light, with a very specific energy and frequency. This quantization explains the distinct spectral lines observed when elements are heated and emit light, and it is fundamental to the stability of atoms, preventing electrons from spiraling into the nucleus. The Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927, is another profound departure from classical intuition. It states that there are certain pairs of properties of a quantum particle that cannot be known simultaneously with arbitrary precision. The more precisely one property is measured, the less precisely the other can be known. The most common example is position and momentum. If you precisely measure a particle's position, you inherently disturb its momentum, making its future trajectory less predictable. This is not a limitation of our measuring instruments, but a fundamental inherent property of nature itself. It means that the universe at its most fundamental level is not deterministic in the classical sense, where knowing all initial conditions allows for perfect prediction of the future. Instead, quantum mechanics provides only probabilities for outcomes. Perhaps the most mind-bending aspect of quantum mechanics is entanglement. This phenomenon occurs when two or more particles become linked in such a way that the quantum state of each particle cannot be described independently of the others, even if they are separated by vast distances. If you measure a property of one entangled particle, such as its spin, you instantaneously know the corresponding property of its entangled partner, regardless of how far apart they are. Albert Einstein famously called this spooky action at a distance, because it seemed to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. However, numerous experiments, particularly those testing Bell's theorem, have definitively confirmed the reality of entanglement, showing that the correlations between entangled particles are stronger than any classical explanation could allow. While entanglement does not allow for faster-than-light communication, as no information can be transmitted faster than light, it highlights a deep, non-local interconnectedness in the quantum fabric of reality. These weird quantum rules are not mere theoretical curiosities, they are the bedrock upon which modern technology is built. The stability of atoms, the behavior of chemical bonds, the operation of lasers, transistors and microchips all rely on quantum mechanical principles. Without quantum mechanics, there would be no chemistry as we know it, no stable matter, no complex molecules, and certainly no life. The universe, in its very construction, embraces these counterintuitive rules, making its existence possible in a way that classical physics could never explain. The strangeness of the quantum world is not a bug, but a feature, a fundamental aspect of the perfect recipe that allows for complexity and consciousness to emerge. The concept of the observer effect in quantum mechanics is one of the most debated and philosophically challenging aspects of modern physics. It refers to the phenomenon where the act of measuring or observing a quantum system appears to fundamentally alter its state, collapsing its multiple possibilities into a single, definite reality. This is not simply about disturbing a system by shining light on it, as one might do to measure a classical object. Rather, it implies that reality itself at the quantum level is not fixed until it interacts with a macroscopic measuring device or environment. This idea raises profound questions about the nature of reality, objectivity, and the role of consciousness, though physicists generally agree that observer in this context refers to an interaction, not necessarily a conscious being. To understand the observer effect, it is essential to revisit the concept of superposition and wave-particle duality. As discussed previously, quantum particles can exist in a superposition of multiple states simultaneously. For example, an electron can be in a superposition of having its spin pointing both up and down, or of passing through two slits at once in the double-slit experiment. This probabilistic state is mathematically described by something called a wave function. The wave function does not represent a physical wave in space, but rather a mathematical description of all the possible states a quantum system can be in, along with the probabilities of finding it in each of those states. The observer effect comes into play when a measurement is made. According to the standard interpretation of quantum mechanics, the act of measurement causes the wave function to collapse. Before the measurement, the particle exists in a superposition of all its possible states. Upon measurement, the wave function instantaneously collapses, and the particle is found in only one of those states, with a probability determined by the wave function. For instance, in the double-slit experiment, when no detector is present at the slits, electrons behave as waves, creating an interference pattern. However, if a detector is placed at the slits to determine which slit each electron passes through, the act of observing or interacting with the electron at the slits causes its wave function to collapse. The electron is then forced into a definite state. It goes through either the left slit or the right slit, and the interference pattern disappears, replaced by a pattern characteristic of classical particles. It is as if the electron knows it is being watched and changes its behavior. This phenomenon leads to what is known as the measurement problem, a central unresolved issue in quantum mechanics. The problem is, what exactly constitutes a measurement? Where is the boundary between the quantum world, where superposition reigns, and the classical world, where definite outcomes are observed? Does the collapse happen when a photon hits the particle, when the signal reaches a detector, when the data is recorded by a computer, or when a conscious mind interprets the data? The standard Copenhagen interpretation, primarily championed by Niels Bohr and Werner Heisenberg, asserts that the wave function is merely a mathematical tool, and reality only becomes definite upon measurement. Before measurement, only probabilities exist, and the act of observation creates the reality we perceive. This interpretation avoids deep philosophical questions by stating that we should not ask what a particle is doing when it is not being observed. However, other interpretations attempt to address the measurement problem in different ways. The many-worlds interpretation, proposed by Hugh Everett III in 1957, suggests that there is no wave function collapse. Instead, every time a measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome. In one universe, the electron went through the left slit. In another, it went through the right. All possibilities are realized in different branches of the universe. This interpretation preserves determinism, but at the cost of an ever-branching multiverse. Another approach is the de Broglie-Bohm theory, or pilot wave theory. developed by Louis de Broglie and later refined by David Bohm. This interpretation proposes that particles always have definite positions, guided by a pilot wave that never collapses. This restores a deterministic objective reality, but introduces non-locality in a different way, where the pilot wave instantaneously influences particles across vast distances. There are also spontaneous collapse theories, which propose that wave function collapse is a real, physical process that happens randomly over time, independent of any observer, rather than being triggered by measurement. The most famous illustration of the measurement problem and the observer effect is Schrödinger's cat. In this thought experiment, a cat is placed in a sealed box with a device that has a 50% chance of releasing a poison. The device is triggered by the decay of a radioactive atom, a quantum event. According to quantum mechanics, until the box is opened, the radioactive atom is in a superposition of having both decayed and not decayed. This means the cat, linked to the atom, is in a superposition of being both alive and dead simultaneously. Only when an observer opens the box does the wave function collapse, and the cat is found to be definitively alive or dead. This thought experiment highlights the absurdity of extending quantum superposition to macroscopic objects, and underscores the profound conceptual difficulty of the measurement problem. Experiments like quantum eraser experiments further deepen the mystery. These experiments involve setting up a double-slit experiment, where information about which path a photon takes is initially recorded. This measurement causes the interference pattern to disappear. However, if the which path information is later erased, without directly interacting with the photon's path, the interference pattern reappears, even if the erasure happens after the photon has supposedly passed through the slits. This suggests that the past behavior of a quantum particle can be influenced by future events, challenging our linear understanding of cause and effect and the very nature of objective reality. The observer effect, therefore, is not just a quirky feature of the quantum world, it is a fundamental challenge to our classical worldview, suggesting that reality might be more fluid and interconnected than we ever imagined. Time, as we experience it, flows relentlessly forward. We remember the past, live in the present, and anticipate the future. A broken glass never spontaneously reassembles itself. A cup of hot coffee always cools down. A person grows older, never younger. This unidirectional progression of time is so fundamental to our existence that we rarely question it. Yet, when we examine the most fundamental laws of physics that govern the universe at the microscopic level, such as Isaac Newton's laws of motion, James Clerk Maxwell's equations for electromagnetism, and the equations of quantum mechanics, they are, for the most part, time-symmetric. This means that these laws would work equally well if time were running backward. If you were to watch a video of individual atoms colliding, you often could not tell if the video was playing forwards or in reverse. The laws governing these tiny interactions do not inherently distinguish between past and future. So, if the microscopic laws are time-symmetric, why does time have such a clear and undeniable direction in our macroscopic world? The answer lies primarily in the second law of thermodynamics and the concept of entropy. Entropy is a measure of disorder, randomness, or the number of possible microscopic arrangements of particles in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time or remain constant, but it can never decrease. This law is not a fundamental law like gravity or electromagnetism. Rather, it is a statistical law. It is overwhelmingly probable that systems will evolve from states of lower entropy, more order, to states of higher entropy, more disorder, simply because there are vastly more ways for a system to be disordered than ordered. Consider everyday examples. If you drop a glass, it shatters into many pieces. This is an increase in entropy, moving from an ordered state, intact glass, to a disordered state, shattered fragments. It is theoretically possible for the pieces to spontaneously reassemble, but the probability of all the atoms and molecules in the glass randomly moving in precisely the right way at the same time to reconstruct the original glass is astronomically small, effectively zero. Similarly, a lump of sugar dissolves in coffee, spreading its molecules throughout the liquid. The reverse process, sugar molecules spontaneously recollecting into a lump at the bottom of the cup, never happens. Heat always flows from a hot object to a cold object, never the other way around, because this process increases the overall entropy of the system. These irreversible processes define the thermodynamic arrow of time. The existence of this thermodynamic arrow of time in our universe is deeply connected to its initial state. For entropy to increase, the universe must have started in an incredibly low entropy, highly ordered state. The Big Bang, roughly 13.8 billion years ago, describes a universe that began as an extremely hot, dense, and remarkably uniform plasma. While incredibly hot, this state was also highly ordered in terms of its gravitational configuration. All the matter and energy were concentrated in a tiny volume, with very little gravitational clumping. This initial low entropy provided the room for entropy to increase over cosmic time, driving the evolution of the universe from a smooth, uniform state to one filled with complex structures like stars, galaxies, and life. If the universe had begun in a high entropy, disordered state, it would have quickly reached a state of thermal equilibrium, where everything is uniformly distributed and nothing interesting happens. There would be no processes, no evolution, and no arrow of time. The origin of this initial low entropy is itself a profound cosmological puzzle, often referred to as the past hypothesis. Why did the Big Bang start with such incredible order? Beyond the thermodynamic arrow, there are other arrows of time that are ultimately linked to it. The cosmological arrow of time refers to the universe's continuous expansion. As the universe expands, its volume increases, matter and energy become more diffuse, and its overall entropy increases. This expansion provides a cosmic direction for time. If the universe were to eventually contract, in a hypothetical big crunch, then the cosmological arrow would reverse, and entropy might decrease in that phase. But our current observations indicate an accelerating expansion. The radiative arrow of time refers to the fact that electromagnetic waves, such as light, always propagate outwards from their source, never converging inwards to a source. A light bulb emits light that spreads out. It does not absorb light from space to become brighter. This is also fundamentally connected to the second law of thermodynamics, as an inward converging wave would represent a highly ordered low entropy state that is statistically improbable to occur spontaneously. Finally, there is the psychological arrow of time, which is our subjective experience of time flowing from past to future. We remember the past, not the future. Our brains are structured to record information from past events, and our actions are aimed at influencing future outcomes. This psychological arrow is almost certainly a consequence of the thermodynamic arrow. The processes of memory formation, learning, and consciousness itself involve increasing the entropy of our brains and their environment. We build memories by creating ordered structures from disordered inputs, but the overall process of living and interacting with the world increases total entropy. The arrow of time is not just an abstract concept, it is what makes the universe dynamic and interesting. It allows for the formation of complex structures, from atoms to galaxies, and for the emergence of life and consciousness. It dictates that cause precedes effect, enabling predictable processes and the very possibility of scientific inquiry. Without the arrow of time, the universe would be a static, unchanging, or randomly fluctuating mess, devoid of the evolution, history, and complexity that define our existence. The fact that time flows in one direction, driven by the relentless march towards increasing disorder, is a fundamental property of our universe that enables everything we perceive and experience. The universe, in its vastness and complexity, presents a compelling paradox. How can such intricate order and structure arise from what seems to be a fundamentally disordered process? The key to understanding this lies in the concept of entropy, a central idea in thermodynamics, the branch of physics that deals with heat and its relation to other forms of energy and work. In simple terms, entropy can be thought of as a measure of disorder, randomness, or the number of ways the components of a system can be arranged. A highly ordered system has low entropy, meaning its components are arranged in a very specific, constrained way. A disordered system has high entropy, meaning its components can be arranged in many different ways, making it more probable. The fundamental principle governing entropy is the second law of thermodynamics, which states that the total entropy of an isolated system can only increase over time, or remain constant, but it can never decrease. This is not a strict law in the same sense as gravity or electromagnetism, which dictate precise forces. Instead, the second law is a statistical law. It tells us that systems naturally tend to evolve from less probable, more ordered states to more probable, more disordered states simply because there are vastly more ways for a system to be disordered than ordered. For instance, if you have a neatly stacked deck of cards, there is only one way for it to be in that specific order. However, there are an enormous number of ways for the cards to be shuffled into a disordered state. Given enough time and random interactions, the deck will almost certainly become disordered. Everyday experiences provide countless examples of the second law in action. A drop of ink placed in a glass of water will spread out and mix evenly, never spontaneously recollecting into a concentrated drop. A hot cup of coffee will cool down to room temperature, never spontaneously heating up by drawing energy from its surroundings. A building, left unattended, will decay and crumble over time, never spontaneously assembling itself into a more ordered structure. These processes are irreversible because the reverse process would require a highly improbable, spontaneous decrease in entropy. The universe as a whole is considered an isolated system, and thus its total entropy is constantly increasing. This relentless march towards greater disorder is what gives time its unidirectional flow, establishing the arrow of time that we perceive. The remarkable puzzle, then, is not that entropy increases, but that the universe began in a state of incredibly low entropy. The Big Bang, approximately 13.8 billion years ago, describes a universe that emerged from an extremely hot, dense, and remarkably uniform state. While the early universe was incredibly hot, its matter and energy were distributed almost perfectly smoothly. This might seem counterintuitive, as we often associate high temperature with disorder. However, in the context of gravity, a smooth, uniform distribution of matter represents a state of very low gravitational entropy. Matter has maximum potential energy when it is uniformly spread out, and minimum potential energy when it is clumped together. Think of a perfectly smooth, unblemished blanket. This is a low entropy state. If you crinkle it up or gather it into lumps, you increase its entropy. Similarly, the early universe was like a perfectly smooth, uncrinkled blanket of matter and energy. This initial low gravitational entropy was absolutely crucial for the subsequent evolution of the universe and the emergence of complexity. It provided the room for entropy to increase over cosmic time, driving the formation of structures. Gravity, acting on the tiny density fluctuations present in the early universe, which were themselves stretched from quantum fluctuations during inflation, began to pull matter together. This clumping of matter into stars, galaxies, and galaxy clusters represents an increase in gravitational entropy, as matter moves from a smooth, uniform distribution to a more clumpy, gravitationally bound, and thus lower potential energy state. Paradoxically, the formation of highly ordered structures like stars, planets, and even living organisms represents local decreases in entropy. A star is a highly ordered system, converting diffuse hydrogen into heavier elements and radiating energy. A living organism, with its intricate biological machinery, is a marvel of order. However, these local decreases in entropy are always paid for by a much larger increase in the entropy of their surroundings. For example, a star produces a tremendous amount of high-entropy radiation as it fuses elements, vastly increasing the overall entropy of the universe. A plant grows by taking in low-entropy sunlight and nutrients, but in doing so it releases high-entropy heat and waste products, contributing to an overall increase in the universe's entropy. Life, therefore, is not a violation of the second law, but rather a temporary localized reversal of entropy, powered by the larger irreversible increase in entropy elsewhere in the cosmos. If the universe had begun in a state of high entropy, for example, if all matter and energy had been uniformly distributed and in thermal equilibrium, like a perfectly mixed, lukewarm soup, then nothing interesting would ever have happened. There would be no temperature differences to drive heat engines, no gravitational potential to form stars, no chemical gradients to power life. the universe would have reached its ultimate heat death almost immediately. The fact that the Big Bang started with such an incredibly low gravitational entropy is a profound puzzle. It is often called the past hypothesis, the hypothesis that the universe was in a very special low entropy state at its beginning. Why was it so special? Why did it start in a state that allowed for such a long and complex journey of increasing disorder, leading to the formation of everything we see, including ourselves? This initial condition is a fundamental prerequisite for our existence, and its origin remains one of the deepest mysteries connecting thermodynamics, cosmology, and the very question of why there is something rather than nothing. The universe, in its fundamental design, appears to be a place of astonishing precision, almost as if it were calibrated with exquisite care for the emergence of complexity and life. This observation is often referred to as the concept of cosmic coincidences, or fine-tuning. It highlights that numerous fundamental physical constants and initial conditions of the universe possess values that fall within an incredibly narrow range, such that if they were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, chemistry, and ultimately life as we know it. These are not merely fortunate accidents. They represent a series of highly specific parameters in a vast landscape of possibilities, making the existence of our universe seem remarkably improbable. One of the most striking examples of fine-tuning involves the strength of the strong nuclear force. This force, which binds protons and neutrons together to form atomic nuclei, is immensely powerful but acts only over incredibly short distances. If the strong force were just a few percent weaker, atomic nuclei beyond hydrogen would be unstable. Protons would repel each other too strongly due to the electromagnetic force, preventing the formation of elements like carbon, oxygen and nitrogen, which are the building blocks of life. The universe would be a monotonous expanse of hydrogen and perhaps some helium. Conversely, if the strong force were just a few percent stronger, protons might bind too readily, perhaps forming stable diprotons, two protons bound together, or other exotic nuclei that would consume all hydrogen in the early universe. This would mean no water, no long-lived stars like our Sun, which rely on hydrogen fusion, and a drastically different, likely lifeless cosmos. The observed strength allows for a diverse range of stable elements and long-lived stars. The mass difference between a proton and a neutron is another crucial cosmic coincidence. A neutron is slightly more massive than a proton. This tiny mass difference, approximately 0.13% of the proton's mass, is vital. If the neutron were even slightly lighter than the proton, all protons in the early universe would have converted into neutrons. This would lead to a universe with no hydrogen, and thus no water, no long-lived stars, and a very different chemistry. If the neutron was significantly heavier, it would have decayed too quickly into a proton before Big Bang nuclear synthesis could produce sufficient helium. The precise mass difference ensures the right balance of protons and neutrons in the early universe, allowing for the formation of hydrogen and helium in the correct proportions, which are essential for stellar evolution and the subsequent creation of heavier elements. The strength of the electromagnetic force relative to the strong force and gravity is also finely tuned. Electromagnetism dictates how electrons orbit atomic nuclei and how atoms form molecules. If it were much stronger, electrons would be pulled too tightly to nuclei, preventing the formation of complex molecules. If it were much weaker, electrons might not form stable orbits, or atoms would be too diffuse. Furthermore, the ratio of the electromagnetic force to gravity is enormous, approximately 10 to the power of 40. This vast difference is essential. Gravity dominates on large scales, forming stars and galaxies, while electromagnetism dominates on atomic scales, allowing for chemistry. If gravity were much stronger relative to electromagnetism, stars would burn out too quickly, or the universe would be dominated by black holes. If electromagnetism were much weaker, matter might not clump into stars and galaxies effectively. Perhaps one of the most celebrated examples of fine-tuning involves the energy levels within carbon and oxygen atomic nuclei, particularly the Hoyle resonance. Carbon, with its 6 protons, is the backbone of all known life. It is primarily produced in the cores of stars when 3 helium nuclei, alpha particles, fuse together. This triple alpha process is inherently difficult because the intermediate step, the fusion of two helium nuclei, forms an unstable beryllium-8 nucleus that quickly decays. For carbon-12 to form in sufficient quantities, there must be a specific energy level, or resonance, within the carbon-12 nucleus that precisely matches the energy of the fusing helium and beryllium nuclei. Sir Fred Hoyle, a British astronomer, predicted this resonance in the 1950s, arguing that its existence was necessary for carbon to be produced in the universe. Without this precise resonance, virtually no carbon would form, making carbon-based life impossible. Similarly, the energy level of oxygen-16 is also critical. It allows oxygen to form from carbon and helium, but it is just slightly off resonance enough to prevent all carbon from being converted into oxygen. This delicate balance ensures the cosmic abundance of both carbon and oxygen, the two most vital elements for life after hydrogen and helium. The cosmological constant, which represents the energy density of empty space, dark energy, is another parameter exhibiting extreme fine-tuning. Its observed value is incredibly small, yet positive, by a factor of approximately 120 orders of magnitude smaller than theoretical predictions from quantum field theory. If the cosmological constant were significantly larger, its repulsive force would have caused the universe to expand so rapidly that matter could never have clumped together to form galaxies, stars, or any stable structures. The universe would have been a desolate, rapidly expanding void. If it were negative and too large, the universe would have collapsed back on itself almost immediately. The fact that its value is so tiny, allowing for both structure formation and accelerated expansion over billions of years, is a profound cosmic coincidence. Even the number of spatial dimensions we inhabit, 3, appears to be finely tuned for complexity. In a universe with only 2 spatial dimensions, complex structures like nervous systems or circulatory systems, which require intricate interconnections without crossing paths, would be difficult or impossible to form. Stable planetary orbits around stars are also problematic in 2 dimensions. In a universe with 4 or more spatial dimensions, the inverse square law of gravity would change, becoming an inverse cube law in 4 dimensions, for instance. This would cause planetary orbits to be unstable, spiraling inward or outward, and would likely prevent the formation of stable atoms, as electrons would not maintain stable orbits around nuclei. The existence of precisely 3 spatial dimensions seems essential for the kind of complex stable structures that underpin life. Faced with the astonishing array of cosmic coincidences and the apparent fine-tuning of the universe's fundamental constants and initial conditions, scientists and philosophers have developed various interpretations, one of the most prominent being the Anthropic principle. This principle, in its various forms, offers a way to understand why the universe appears to be so exquisitely suited for life, not by invoking a designer, but by considering the necessary conditions for the existence of observers like ourselves. It essentially turns the question around. Rather than asking why the universe is fine-tuned, it asks what kind of universe we must inhabit given that we exist to observe it. The most widely accepted and least controversial version is the weak anthropic principle, DWAP. This principle states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist places where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In simpler terms, the WAP is a selection effect. If there were many universes or many regions within a single, vastly larger universe, each with different physical laws or different values for fundamental constants, then only those universes or regions that allow for the formation of stars, planets, and complex chemistry would be capable of hosting life. We, as observers, necessarily find ourselves in one of these life-permitting universes or regions. It is like finding yourself on a habitable planet with liquid water and a breathable atmosphere. You wouldn't find yourself on a barren, airless rock, so observing a habitable planet is not surprising. It's a prerequisite for your presence. The WAP does not explain why the universe is fine-tuned, but rather explains why we observe it to be fine-tuned. It is a statement about our observational bias. The WAP gains significant explanatory power when combined with the multiverse hypothesis. If our universe is not the only one, but merely one among an enormous, perhaps infinite ensemble of universes, then the apparent fine-tuning becomes less miraculous. In a multiverse, each universe could have different physical laws, different fundamental constants, and different initial conditions. In such a scenario, it is statistically inevitable that some universes would happen to have the precise combination of parameters necessary for the emergence of life. Our universe would simply be one of those rare, fortunate ones. We exist here because this is one of the few places where we could exist. The multiverse thus provides a framework for the UPWAP to function as a plausible scientific explanation for fine-tuning, shifting the question from "why is this universe fine-tuned?" to "how did the multiverse generate so many variations?" Different theoretical models propose various types of multiverses. One prominent idea is the inflationary multiverse, arising from the theory of cosmic inflation. If inflation, the rapid expansion in the very early universe, is eternal, it could continuously spawn new bubble universes, or pocket universes. Each of these bubbles could potentially have different physical laws and constants, depending on how the scalar field driving inflation settles down. Another concept comes from string theory, which suggests that our universe exists on a brane within a higher dimensional space. String theory also predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants. If all these states are realized in different universes, then the fine-tuning of our universe could be explained by our selection bias within this landscape. A more controversial version is the strong anthropic principle, SAP. This principle states that the universe must have those properties which allow life to develop within it at some stage. This goes beyond mere observation and implies a deeper necessity or compulsion for the universe to be life-permitting. It suggests that the laws of physics are not just randomly chosen, but are somehow compelled to be life-permitting. Some interpretations of the SAPI verge into teleological or even theological territory, implying that the universe was somehow designed or destined for life. However, most scientific discussions of the SAPI interpret it as a stronger form of the WUP, suggesting that the very existence of fundamental laws or the initial conditions of the universe are such that they must lead to observers. The Anthropic principle, particularly the multiverse interpretation, faces several criticisms. One major critique is its lack of empirical testability. If other universes exist, they are, by definition, beyond our observable horizon and cannot be directly accessed or measured. This makes the multiverse hypothesis difficult to falsify or verify through traditional scientific methods, leading some to argue that it falls outside the realm of science. Another criticism is that it shifts the problem of fine-tuning rather than solving it. If our universe is fine-tuned, then what about the multiverse itself? Is the multiverse fine-tuned to produce universes like ours? This can lead to an infinite regress of explanations. Furthermore, some argue that the anthropic principle is a tautology, a statement that is true by definition, and therefore provides no new information. Of course, we must find ourselves in a universe that allows for our existence. This doesn't explain why such a universe exists in the first place. Despite these criticisms, the anthropic principle, especially the weak version combined with the multiverse, offers a compelling framework for addressing the fine-tuning problem without resorting to supernatural explanations. It transforms the apparent improbability of our universe into a statistical inevitability within a larger cosmic landscape. While it may not provide a definitive answer to the ultimate why question, it offers a powerful scientific perspective on why the universe appears to have a perfect recipe for life. By emphasizing the crucial role of observers in selecting the specific reality they inhabit, it forces us to confront the possibility that our universe might be just one of countless others, each a different roll of the cosmic dice. The universe, as observed by astronomers and physicists, appears to be remarkably fine-tuned for the existence of life. Numerous fundamental physical constants, such as the strength of gravity, the mass of the electron, and the initial expansion rate of the cosmos, possess values that fall within an incredibly narrow range. If these values were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, complex chemistry, and ultimately, life as we know it. This apparent cosmic coincidence has led to deep philosophical and scientific questions about why our universe seems to have such a perfect recipe. one of the most compelling and actively discussed theoretical frameworks attempting to address this fine-tuning problem is the multiverse theory. This concept proposes that our universe is not unique, but is merely one of an enormous, perhaps infinite number of universes, each potentially possessing different physical laws, fundamental constants, and initial conditions. The core idea behind the multiverse is to transform the apparent improbability of our universe's fine-tuning into a statistical inevitability. If there are countless universes, each with a different set of physical parameters, then it becomes statistically probable, even guaranteed, that at least one of these universes would happen to have the precise combination of values necessary for the formation of stars, planets, and the emergence of life. In this scenario, our existence as observers means we necessarily find ourselves in one of these rare, life-permitting universes. This is the essence of the weak Anthropic principle, which states that we observe the universe to be fine-tuned because only such a universe could support our existence. The multiverse provides the vast ensemble of possibilities required for the Anthropic principle to be a plausible explanation, rather than a mere tautology. The concept of a multiverse arises from various theoretical extensions of our current understanding of physics, rather than being a single, unified theory. One prominent source of multiverse ideas stems from cosmic inflation, a widely accepted theory describing an extremely rapid, exponential expansion of the universe in its earliest moments. While standard inflation explains many features of our universe, such as its flatness and uniformity, some models of inflation, particularly those involving a scalar field that drives the expansion, suggest that inflation might not end everywhere simultaneously. Instead, quantum fluctuations in this field could cause inflation to stop in some regions, forming bubbles of space-time that become individual universes, while in other regions, inflation continues indefinitely, spawning new bubbles. This leads to the idea of eternal inflation, where an infinitely branching, self-reproducing inflationary space-time continuously generates new universes. Each of these bubble universes could potentially have different physical laws and constants, depending on how the inflaton field settles down within that particular bubble. Another theoretical avenue for the multiverse comes from string theory and its extension, M-theory. String theory attempts to unify all fundamental forces and particles by proposing that the most basic constituents of reality are not point-like particles but tiny, one-dimensional vibrating strings. A key feature of string theory is that it requires the existence of more than the familiar four space-time dimensions, 3 spatial and 1 temporal. For the theory to be consistent, it often predicts 10 or 11 dimensions. The reason we only perceive 4 dimensions is that the extra dimensions are thought to be compactified, or curled up into incredibly tiny unobservable spaces. The way these extra dimensions are curled up, known as the Calabi-Yau manifold, can vary in an enormous number of ways, estimated to be as high as 10 to the power of 500. Each distinct way of compactifying the extra dimensions could correspond to a different set of physical laws and fundamental constants in the 4 large dimensions we experience. This vast number of possibilities is often referred to as the landscape of string theory. If each point in this landscape represents a different universe, then the universe we inhabit is simply one of the countless possibilities within this string landscape. The implications of a multiverse are profound. Firstly, it offers a purely naturalistic explanation for the universe's fine-tuning, reducing the need to invoke supernatural or teleological explanations. If there are infinite rolls of the cosmic dice, then it is no longer a miracle that one particular roll came up with the winning numbers for life. Secondly, it challenges the traditional view of our universe as the entirety of existence. Our observable universe, vast as it is, might just be a tiny speck within a much larger, incomprehensibly immense multiverse. Thirdly, it raises new questions about the origin and nature of the multiverse itself. If our universe requires an explanation for its existence, does the multiverse also require one? This can lead to an infinite regress of explanations, or suggest that the multiverse is a brute fact that simply exists without further cause. However, the multiverse theory also faces significant challenges and criticisms. The most prominent challenge is its lack of direct empirical testability. By definition, other universes in many multiverse models are causally disconnected from our own, meaning we cannot send signals to them, observe them directly, or interact with them. This makes it incredibly difficult, if not impossible, to gather direct observational evidence to confirm or refute their existence through traditional scientific methods. Some physicists argue that this lack of testability places the multiverse hypothesis outside the realm of empirical science, relegating it to philosophy or metaphysics. Proponents, however, argue that while direct observation might be impossible, indirect evidence could emerge, such as specific patterns in the cosmic microwave background radiation that might hint at collisions with other universes, or the discovery of new particles predicted by theories that also lead to a multiverse. Another challenge is the measure problem in infinite multiverses. If there are an infinite number of universes, how do we assign probabilities to different outcomes or properties? If every possible universe exists an infinite number of times, then any specific event, no matter how improbable, occurs infinitely often. This makes it difficult to make predictions or test the theory, as any outcome could be explained by some universe existing. Despite these challenges, the multiverse theory remains a powerful and elegant conceptual framework for addressing some of the deepest puzzles in cosmology, particularly the apparent fine-tuning of our universe, by embedding our reality within a much grander and more diverse cosmic tapestry. The concept of bubble universes emerges primarily from the theory of cosmic inflation, a cornerstone of modern cosmology that describes an extremely rapid, exponential expansion of the universe in its earliest moments. While the standard Big Bang model explains the universe's evolution from a hot, dense state, it faced several puzzles such as the flatness problem, why the universe's geometry is so precisely flat, the horizon problem, why distant regions of the universe that were never in causal contact have the same temperature, and the monopole problem, why no magnetic monopoles predicted by some grand unified theories are observed. Cosmic inflation, proposed in the 1980s, elegantly solves these problems by positing a brief but incredibly powerful burst of expansion. During inflation, which is thought to have occurred between approximately 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe expanded by an enormous factor, perhaps as much as 10 to the power of 26 or more. This rapid stretching smoothed out any initial irregularities, making the universe flat and uniform on large scales. The energy driving this expansion is typically attributed to a hypothetical scalar field, often called the inflaton field. This field possessed a high energy density that acted as a repulsive gravitational force, pushing space-time apart at an accelerating rate. At the end of inflation, the inflaton field decayed, converting its energy into the hot, dense soup of particles and radiation that constituted the initial conditions for the standard Big Bang expansion. The idea of bubble universes arises when we consider the possibility of eternal inflation. In many models of inflation, the inflaton field does not decay uniformly or simultaneously across all of space-time. Instead, quantum fluctuations within the inflaton field can cause inflation to stop in certain localized regions, while in other regions the field continues to fluctuate and drive inflation. When inflation stops in a particular region, that region reheats and becomes a distinct bubble universe that begins to expand and evolve according to the standard Big Bang model. However, the surrounding space continues to inflate, creating new regions where inflation can end, thus spawning more bubble universes. This process can continue indefinitely, leading to an infinitely branching, self-reproducing inflationary space-time, a multiverse composed of an endless number of these causally disconnected bubble universes. Each of these bubble universes, once formed, is essentially a separate Big Bang event. From the perspective of an observer inside one of these bubbles, their universe would appear to have originated from a singular point and expanded just like our own. However, from the perspective of the larger, eternally inflating space-time, these bubbles are constantly being created and expanding within a larger, non-ending inflationary background. A key feature of these bubble universes is that they can possess different physical properties. The way the inflaton field decays and settles into a stable vacuum state can vary from one bubble to another. Each vacuum state corresponds to a different set of fundamental physical laws and constants. For example, in one bubble universe, the strength of gravity might be slightly different. In another, the mass of the electron might be larger, or the cosmological constant dark energy might have a different value. Some bubble universes might even have a different number of effective spatial dimensions, or different types of fundamental particles. This vast diversity of properties across the ensemble of bubble universes is what makes the eternal inflation model a powerful candidate for explaining the fine-tuning of our own universe. If there are an infinite number of such bubbles, each with a random assortment of physical laws, then it is statistically inevitable that some of them will happen to have the precise combination of parameters necessary for the formation of stars, galaxies, chemistry, and ultimately, life. We, as observers, necessarily find ourselves in one of these rare life-permitting bubbles. The scale of these bubble universes is immense. Each individual bubble can be unimaginably vast, perhaps even infinite in extent, and they are separated from each other by regions of still inflating space, which expands so rapidly that it prevents any interaction or communication between the bubbles. This means that even if another bubble universe were to collide with ours, we would likely never know it, as the event would occur in a region of space-time that is receding from us faster than the speed of light. While the concept of bubble universes arising from eternal inflation is a highly theoretical one, it emerges naturally from the mathematical framework of inflationary cosmology, which is widely accepted for its ability to solve the problems of the standard Big Bang model. It provides a compelling, naturalistic explanation for the apparent fine-tuning of our universe without resorting to a designer. However, it also presents significant challenges. The lack of direct observational evidence for other bubble universes remains a major hurdle, as their causal disconnection makes them inherently unobservable. Furthermore, the measure problem in infinite multiverses, which deals with how to assign probabilities to different outcomes in an infinite ensemble, remains an active area of research and debate. Despite these challenges, the idea of bubble universes offers a fascinating and powerful perspective on the origin and nature of our cosmos, suggesting that our universe might be just one tiny, habitable pocket within an infinitely larger, eternally expanding cosmic foam. The hypothesis that our universe, and everything within it, is in fact a highly sophisticated computer simulation is a fascinating and profoundly unsettling idea that challenges our fundamental understanding of reality. This concept, often explored in science fiction, has gained traction in philosophical and scientific circles, primarily driven by arguments about the potential capabilities of future advanced civilizations. It suggests that our perceived reality is not a fundamental base reality, but rather an artificial construct, much like a virtual reality game, designed and run by a more technologically advanced civilization existing in a higher level reality. The most compelling argument for the simulation hypothesis was put forth by philosopher Nick Bostrom in 2003. His argument is based on a probabilistic trilemma. At least one of three propositions must be true. First, that civilizations almost never reach a post-human stage capable of running highly realistic simulations. This could be due to self-destruction, technological stagnation, or some other limiting factor. Second, that post-human civilizations, if they do arise, almost never run a significant number of ancestor simulations. This implies they might have no interest in simulating their past, or they might consider it unethical, or they might simply prefer other forms of entertainment or research. Third, that we are almost certainly living in a simulation. If post-human civilizations are common, and if they are interested in running ancestor simulations, then the number of simulated realities would vastly outnumber the single base reality. Therefore, statistically, it would be far more probable that we exist within one of these many simulations rather than in the single original reality. The argument relies on the assumption that the technological capacity to create highly realistic, conscious agent-filled simulations is achievable. Given the rapid advancements in computing power observed over the past decades, such a future seems plausible, at least conceptually. If our own civilization continues to advance at its current pace, it is conceivable that within centuries or millennia, we might possess the computational resources to simulate entire universes or historical periods with conscious beings. If we can, then it stands to reason that other, older, more advanced civilizations could already be doing so. While the simulation hypothesis is primarily a philosophical argument, some proponents point to certain features of our universe that, while not definitive proof, could be interpreted as evidence or glitches consistent with a simulated reality. One such feature is the fine-tuning of the universe's fundamental constants. As discussed in previous chapters, the precise values of gravity, electromagnetism, particle masses, and the cosmological constant seem perfectly calibrated for life. In a simulated universe, these parameters could simply be the settings chosen by the simulators to create a particular kind of environment or to achieve specific outcomes. This would explain the fine-tuning without resorting to chance or a divine creator. Another intriguing aspect is the quantum nature of reality. The probabilistic behavior of particles, the wave-particle duality, and the observer effect, where particles only take on definite states upon measurement, could be interpreted as computational optimizations. In a simulation, rendering every single particle in the universe at all times would be computationally expensive. Instead, the simulation might only render or compute the state of a particle when it is observed or interacted with. Much like a video game only renders the parts of the environment visible to the player. The inherent discreteness of reality at the Planck scale, the smallest possible units of length and time, could also be seen as the pixelation or computational resolution limit of the simulation. The mathematical nature of physical laws is also cited. The universe operates according to elegant and precise mathematical equations. This could simply be a reflection of its underlying computational code. Conservation laws, such as the conservation of energy and momentum, could be built-in rules of the simulation to ensure consistency. The finite speed of light could be a computational constraint, a maximum processing speed within the simulated environment. The Fermi paradox, which questions why we haven't detected any evidence of alien civilizations despite the high probability of their existence, could also be explained by the simulation hypothesis. Perhaps our simulation is limited to our observable universe, or other civilizations are simply not simulated within our particular instance. The philosophical implications of living in a simulated reality are profound. It raises questions about the nature of consciousness, free will, and purpose. If our reality is simulated, are our thoughts and emotions truly our own, or are they part of the program? What is the purpose of the simulation? Are we historical ancestors, experimental subjects, or simply entertainment? The identity of the simulators also becomes a question. Are they also simulated? This could lead to an infinite regress of simulations within simulations. However, even if we are simulated, our experiences, emotions, and relationships are real within the simulation. The suffering and joy we experience are not diminished by the fact that our reality might be running on a computer. Proving or disproving the simulation hypothesis is incredibly difficult. Direct evidence is unlikely, as the simulators would presumably make the simulation indistinguishable from base reality. Scientists might look for bugs or glitches in the fabric of reality, computational limits being hit, or subtle anomalies that suggest an artificial construct. However, any such anomaly could also be explained by new, undiscovered physics. Ultimately, the simulation hypothesis remains a powerful thought experiment that forces us to critically examine the nature of our existence and the limits of our perception, pushing the boundaries of what we consider real. The universe, in its profound complexity and underlying order, speaks a language that transcends human spoken words, the language of mathematics. From the smallest subatomic particles to the grandest cosmic structures, the fundamental workings of reality appear to be governed by precise mathematical laws and relationships. This pervasive mathematical nature of the cosmos is not merely a convenient tool for scientists to describe phenomena, it seems to be an intrinsic property of existence itself, leading to deep philosophical questions about why mathematics is so incredibly effective at describing the natural world. For centuries, thinkers have pondered this remarkable connection. Ancient Greek philosophers like Pythagoras believed that numbers held the key to understanding the universe, seeing mathematical ratios in musical harmony and celestial motions. Later, in the 17th century, Galileo Galilei famously asserted that the book of nature is written in the language of mathematics. This insight proved prescient, as the scientific revolution that followed was built upon the foundation of mathematical descriptions of physical reality. Consider Isaac Newton's laws of motion and universal gravitation, formulated in the late 17th century. These laws, expressed as elegant mathematical equations, precisely describe how objects move under the influence of forces and how masses attract each other. Newton's mathematical framework allowed for the accurate prediction of planetary orbits, the trajectory of projectiles, and the behaviour of tides, ushering in an era of unprecedented scientific predictability. His work demonstrated that the seemingly chaotic movements of the heavens and the seemingly simple motions on Earth were governed by the same universal mathematical principles. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, again through a set of powerful mathematical equations. Maxwell's equations not only described all known electrical and magnetic phenomena, but also predicted the existence of electromagnetic waves, which travel at the speed of light. This mathematical prediction was later confirmed by Heinrich Hertz's experiments in the late 1880s, demonstrating that light itself is an electromagnetic wave. This was a triumph of mathematical reasoning, revealing a deeper unity in nature that was not immediately apparent through observation alone. The 20th century brought even more profound mathematical revelations. Albert Einstein's theories of special and general relativity, developed in the early 1900s, fundamentally reshaped our understanding of space, time, gravity, and energy. These theories are expressed in highly sophisticated mathematical frameworks, particularly differential geometry for general relativity. Einstein's equations describe gravity not as a force, but as the curvature of spacetime caused by mass and energy. These equations predicted phenomena such as the bending of light by massive objects, the existence of gravitational waves, detected directly in 2015, a century after their prediction, and the precise orbital precession of Mercury, all of which have been confirmed with extraordinary accuracy. Similarly, quantum mechanics, the theory describing the behaviour of matter and energy at the atomic and subatomic scales, is inherently mathematical. Concepts like wave functions, probability amplitudes, and the quantization of energy are all expressed using advanced mathematical tools, including linear algebra and complex numbers. Quantum mechanics predicts the discrete energy levels of atoms, the behaviour of elementary particles, and the outcomes of particle interactions with astonishing precision. Many of its predictions, such as the existence of antimatter, predicted by Paul Dirac's relativistic quantum equation in 1928 and discovered in 1932, and the Higgs boson, predicted by the Standard Model and discovered in 2012, were made purely through mathematical reasoning before experimental verification. This consistent success of mathematics in describing and predicting the physical world has led many to ponder its deeper significance. Eugene Wigner, a Nobel laureate in physics, famously wrote about the unreasonable effectiveness of mathematics in the natural sciences in 1960. He marvelled at how abstract mathematical concepts, often developed for purely intellectual reasons without any immediate physical application in mind, later turn out to be precisely what is needed to describe fundamental aspects of the universe. For example, group theory, a branch of abstract algebra, found unexpected applications in describing the symmetries of elementary particles and the conservation laws that govern their interactions. Is mathematics invented by the human mind, a useful language we create to categorize and understand the world, or is it discovered, an inherent structure of reality that exists independently of human consciousness? The remarkable predictive power and universal applicability of mathematics in physics suggests that it might be more than just a human construct. It implies that the universe itself is fundamentally structured in a mathematical way, that its laws are not arbitrary, but follow a deep, elegant, and consistent mathematical logic. The presence of symmetries in nature, which are beautifully described by mathematics, further reinforces this idea. Symmetries in physical laws often correspond to conservation laws. For example, the symmetry of physical laws under translation in time leads to the conservation of energy, and symmetry under translation in space leads to the conservation of momentum. These deep connections between abstract mathematical symmetries and conserved physical quantities reveal a profound mathematical elegance woven into the fabric of space-time. The universe's adherence to mathematical laws provides a framework for its predictability and order. Without this underlying mathematical structure, the cosmos would be chaotic and unpredictable, making scientific inquiry impossible. The fact that we can formulate theories, make predictions, and consistently verify them through observation and experiment is a testament to the universe's inherent mathematical coherence. This mathematical language is not just a description of what is, it is often a guide to what must be, revealing hidden truths about reality before they are directly observed. It suggests that the universe is not just a collection of random events, but a system built upon a foundation of logical and consistent mathematical principles, making its very existence and its capacity for complexity a profound mathematical marvel. Our everyday experience of the universe is confined to 3 spatial dimensions: length, width, and height, and 1 temporal dimension, time. We move forward and backward, up and down, left and right, and always forward in time. This 4-dimensional space-time continuum, as described by Albert Einstein's theories of relativity, forms the familiar stage upon which all cosmic events unfold. However, many cutting-edge theories in modern physics propose the existence of additional dimensions beyond these familiar 4. These extra dimensions are not merely speculative concepts. They arise naturally from attempts to unify the fundamental forces of nature and to solve some of the deepest puzzles in physics, such as why gravity is so much weaker than the other forces. The idea of extra dimensions is not new. In the early 20th century, shortly after Einstein published his general theory of relativity, Theodore Kaluza and Oscar Klein independently proposed a theory that attempted to unify gravity and electromagnetism by introducing a 5th dimension. Their Kaluza-Klein theory suggested that if the universe had an extra spatial dimension, and if that dimension were curled up into a tiny, unobservable circle, then gravity propagating in this 5-dimensional space-time would appear, from our 4-dimensional perspective, to manifest as both gravity and electromagnetism. The strength of the electromagnetic force would be related to the size of this curled-up dimension. This was a groundbreaking idea, showing that seemingly disparate forces could emerge from a higher dimensional geometry. While Kaluza-Klein theory ultimately failed to fully unify all forces and predict the existence of all particles, it laid the conceptual groundwork for later theories involving extra dimensions. The key to understanding how extra dimensions could exist without being directly observable is the concept of compactification. Imagine a long, thin garden hose. From a distance, it looks like a 1-dimensional line. But if you get very close, you can see that it has a 2nd dimension, its circumference, curled up into a small circle. Similarly, physicists propose that extra dimensions might be curled up, or compactified, into incredibly tiny microscopic spaces, far too small for us to perceive directly with our current technology. These dimensions could be curled up into incredibly complex geometric shapes, often referred to as Calabi-Yau manifolds in string theory. The specific geometry of these curled-up dimensions would then dictate the fundamental physical laws and constants that we observe in our 4 large dimensions. The most prominent theory that necessitates extra dimensions is string theory, and its more encompassing framework, M-theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, 1-dimensional vibrating strings, unimaginably small, roughly 10 to the power of minus 35 meters, the Planck length. Different vibration modes of these strings correspond to different fundamental particles, such as electrons, quarks, and photons. For string theory to be mathematically consistent and free of anomalies, it requires the existence of 10 spacetime dimensions, 9 spatial and 1 temporal. M-theory, which unifies various string theories, requires 11 spacetime dimensions. The extra 6 or 7 spatial dimensions are thought to be compactified, curled up into complex Calabi-Yau shapes. The specific way these extra dimensions are compactified is crucial, as it determines the properties of the particles and forces we observe in our 4-dimensional world. There are an enormous number of ways these dimensions can be curled up, estimated to be as high as 10 to the power of 500 different possible geometries. Each of these geometries would correspond to a different set of physical laws and constants. This vast array of possibilities is often referred to as the string landscape, or the multiverse landscape. In this context, our universe, with its specific fine-tuned laws, is simply one particular realization within this enormous landscape of possibilities, arising from a specific compactification of the extra dimensions. Another fascinating idea involving extra dimensions comes from brain cosmology, particularly models like the Randall-Sundrum models proposed in the late 1990s. In these models, our entire four-dimensional universe is envisioned as a brain, a higher dimensional membrane, embedded within a larger, higher dimensional space called the bulk. In this scenario, ordinary matter and the fundamental forces, electromagnetism, the strong force and the weak force, are confined to our brain. However, gravity, unlike the other forces, is hypothesized to be able to propagate into the higher dimensional bulk. This leakage of gravity into extra dimensions could explain why gravity appears so much weaker than the other fundamental forces from our four-dimensional perspective. The gravitational force we experience is only a fraction of its true strength, as much of its influence is diluted by spreading into the extra dimensions. This could potentially solve the hierarchy problem, which is the vast discrepancy between the gravitational scale and the electro-weak scale, the energy scale at which electromagnetism and the weak force unify. The search for experimental evidence of extra dimensions is a major frontier in physics. One approach involves looking for deviations from Newton's inverse square law of gravity at very small distances. If extra dimensions exist and gravity can propagate into them, then gravity's strength should increase more rapidly than the inverse square law at distances comparable to the size of these extra dimensions. Current experiments have tested gravity down to microscopic scales, roughly tens of micrometers, and have so far found no deviations, placing limits on the size of any large extra dimensions. Another avenue is to search for Kaluza-Klein particles at high-energy particle accelerators like the Large Hadron Collider. If extra dimensions are real, particles could have momentum in these curled-up dimensions, appearing to us as heavier versions of known particles. Detecting such particles would be a strong indicator of extra dimensions. Furthermore, some theories suggest that extra dimensions could affect the propagation of gravitational waves, offering another potential avenue for detection. If extra dimensions truly exist, they would radically alter our understanding of the universe. Our familiar four-dimensional space-time would be merely a slice or a projection of a much grander, higher dimensional reality. This would not only provide a framework for unifying all the fundamental forces, but also offer a compelling explanation for the fine-tuning of our universe's properties within the vast landscape of possibilities arising from different compactifications. The existence of dimensions beyond our perception would mean that the universe is even more intricate and mysterious than we currently imagine, constantly pushing the boundaries of our knowledge. The holographic principle is one of the most profound and counterintuitive ideas to emerge from theoretical physics in recent decades, suggesting that our three-dimensional reality might be, in some sense, a projection from a two-dimensional surface. The concept derives its name from a hologram, a two-dimensional photographic plate that encodes three-dimensional information, allowing a full three-dimensional image to be reconstructed when illuminated correctly. In physics, the holographic principle posits that the description of a volume of space can be thought of as encoded on its boundary, much like a hologram. This means that all the information contained within a region of space, including everything inside it, could be entirely represented by data existing on its two-dimensional surface. This radical idea first emerged from the study of black holes in the 1970s and 80s. Stephen Hawking's work on black hole radiation and Jacob Bekenstein's insights into black hole entropy were pivotal. Bekenstein proposed that the entropy of a black hole, a measure of its internal disorder, or the amount of information it contains, is not proportional to its volume, as one might intuitively expect for a three-dimensional object. Instead, he argued that a black hole's entropy is proportional to the area of its event horizon, the two-dimensional boundary beyond which nothing, not even light, can escape. This was a revolutionary idea because it implied that the maximum amount of information that can be contained within a region of space scales, with its boundary area, not its volume. This concept was further developed by Gerard 't Hooft and Leonard Susskind in the 1990s, who generalized it into the holographic principle. They argued that if the maximum entropy of a region of space scales with its boundary area, it implies that the fundamental degrees of freedom, the basic bits of information that describe everything, are not located throughout the volume but are instead stored on the boundary. It's as if the entire three-dimensional reality of the black hole's interior is somehow encoded on its two-dimensional surface. This is deeply counterintuitive because our everyday experience tells us that a larger volume can hold more information than a smaller surface. For example, a three-dimensional book contains more information than its two-dimensional cover. The holographic principle suggests that at the most fundamental level, this intuition is wrong for space-time itself. The most concrete and powerful realization of the holographic principle comes from the AD-CFT correspondence, or anti-de Sitter conformal field theory correspondence, sometimes called Maldacena duality, proposed by Juan Maldacena in 1997. This is a profound mathematical conjecture that states that a theory of gravity, specifically string theory, in a particular type of curved spacetime called anti-de Sitter space, is mathematically equivalent to a quantum field theory, like those describing particles and their interactions, living on its boundary, which has one fewer dimension. For example, a theory of gravity in a five-dimensional anti-de Sitter space is equivalent to a four-dimensional quantum field theory living on its boundary. This correspondence is a duality because it provides two entirely different yet mathematically equivalent ways to describe the same physical reality. One description involves gravity and extra dimensions, while the other involves quantum particles and forces in a lower dimension. It's like having two different languages that perfectly describe the same set of phenomena. The AD-CFT correspondence has been incredibly fruitful for theoretical physicists because it allows them to use the well-understood tools of quantum field theory to study difficult problems in quantum gravity and vice versa. For instance, problems in strongly interacting quantum systems, like those found in high-temperature superconductors, can be mapped to simpler problems in gravity in a higher dimension. The implications of the holographic principle for our own universe are profound, though it is important to note that the AD-CFT correspondence applies to anti-de Sitter space, which has a negative cosmological constant, whereas our universe has a positive cosmological constant, dark energy, and is expanding. However, many physicists believe that the holographic principle is a more general feature of quantum gravity, and that some form of it might apply to our universe as well. If the holographic principle applies to our universe, it would mean that all the information describing our four-dimensional spacetime and everything within it could, in principle, be encoded on a distant three-dimensional boundary. This does not necessarily mean that we live in a computer simulation in the way discussed in the previous chapter, but it implies a deep and unexpected relationship between space, information, and gravity. It suggests that the fundamental reality might not be what we perceive as three-dimensional space, but rather a more fundamental, information-theoretic structure residing on a boundary. Our perceived reality would then be an emergent phenomenon, a holographic projection from this underlying information. This idea challenges our intuitive understanding of space as a fundamental container. Instead, space itself might be an emergent property, arising from the entanglement of quantum degrees of freedom on a boundary. It suggests that the universe has a finite amount of information, and this information is stored on its surface, much like a cosmic hard drive. While direct experimental verification of the holographic principle in our universe remains a distant goal, it continues to be a powerful guiding principle in the search for a unified theory of quantum gravity, offering a radical new perspective on the fundamental nature of reality and the very fabric of space-time. It hints that the universe's existence might be an intricate dance of information, projected into the dimensions we perceive. At the very frontiers of our understanding of the universe lies a realm of existence so incredibly tiny and fleeting that our current theories of physics begin to break down. This is the Planck scale, a set of fundamental units of measurement, length, time, mass, and temperature, derived solely from universal physical constants, the speed of light, the gravitational constant, and the reduced Planck constant, which relates to quantum mechanics. These units, named after the pioneering German physicist Max Planck, who first introduced them in 1900, are not arbitrary. They represent the natural scales at which the effects of quantum mechanics and general relativity become equally important and inextricably intertwined. The Planck length is the smallest possible unit of length that has any physical meaning. It is approximately 1.6 times 10 to the power of minus 35 meters. To put this into perspective, if an atom were expanded to the size of the entire observable universe, a Planck length would still be smaller than a single atom. At distances smaller than the Planck length, the very fabric of space-time is theorized to become so turbulent and foamy due to quantum fluctuations that our usual concepts of smooth space and time cease to apply. It is at this scale that the quantum nature of gravity, often referred to as quantum foam, is expected to manifest. Our current understanding of space-time based on general relativity describes it as a smooth, continuous manifold. However, at the Planck length, this smooth picture is expected to dissolve into a chaotic, probabilistic quantum realm. The Planck time is the smallest unit of time, approximately 5.4 times 10 to the power of minus 44 seconds. This is the shortest possible duration that has any physical significance. It represents the time it would take for light to travel one Planck length. In the context of the Big Bang, the Planck epoch, which lasted from the beginning of the universe up to one Planck time, is the earliest moment about which we can even theoretically speculate. Before this time, or within this incredibly brief interval, our current laws of physics are insufficient to describe what was happening. The universe was so hot and dense that quantum gravitational effects dominated, and space-time itself was likely in a state that defies our conventional understanding. The Planck mass is approximately 2.17 times 10 to the power of minus 8 kilograms, which is roughly the mass of a flea egg. While this might seem like a macroscopic mass compared to elementary particles, it is the mass at which a particle's Compton wavelength, a quantum mechanical property related to its size, becomes equal to its Schwarzschild radius, the radius at which it would become a black hole according to general relativity. In essence, a particle with the Planck mass, if compressed to the Planck length, would become a black hole. This unit is significant because it represents the scale at which the quantum effects of gravity become as strong as the gravitational force itself. Finally, the Planck temperature is an incredibly high temperature, approximately 1.4 times 10 to the power of 32 Kelvin. This is the maximum theoretical temperature, representing the temperature of the universe at the Planck time. At such extreme temperatures, all known fundamental forces are believed to have been unified, and particles would have possessed energies far beyond anything we can recreate in laboratories. The significance of the Planck scale lies in the fact that it marks the boundary where our two most successful yet incompatible theories of physics, general relativity, describing gravity in the large-scale universe, and quantum mechanics, describing particles and forces at the microscopic level, both become relevant and equally important. However, these two theories, in their current forms, are not easily reconciled. General relativity describes gravity as the curvature of a smooth space-time, while quantum mechanics describes particles and forces in terms of discrete quanta and probabilities. When one attempts to apply quantum mechanics to gravity, the calculations break down, leading to infinities that cannot be resolved. This fundamental incompatibility is the core reason why we lack a complete theory of quantum gravity. At the Planck scale, the very concepts of space and time as continuous entities may cease to be valid. Instead, space-time might be granular or foamy, composed of discrete units, much like a digital image is composed of pixels. This implies that there is a fundamental limit to how finely we can probe reality. We cannot meaningfully ask what happens at distances smaller than the Planck length, or during intervals shorter than the Planck time, because the very notions of space and time lose their conventional meaning. The breakdown of physics at the Planck scale represents the ultimate edge of knowledge in our quest to understand the universe. It is the realm where the most fundamental questions about the origin of space-time, the nature of reality, and the unification of all forces must ultimately be answered. Theories like string theory and loop quantum gravity are attempts to construct a theory of quantum gravity that can describe physics at this extreme scale, providing a consistent framework that incorporates both general relativity and quantum mechanics. Understanding the Planck scale is not just an academic exercise, it is essential for a complete picture of the universe, including its earliest moments during the Big Bang and the ultimate nature of its existence. Despite the monumental achievements of science in unraveling the mysteries of the cosmos, humanity stands at a precipice, gazing into a vast expanse of the unknown. Our current scientific understanding, while profound, is far from complete. There are fundamental questions about the universe that remain unanswered, major phenomena that defy our current theoretical frameworks, and vast swathes of reality that lie beyond the reach of our present observational capabilities. This edge of knowledge is not a sign of failure, but rather a testament to the immense complexity of the universe and the ongoing nature of scientific inquiry. One of the most glaring gaps in our understanding is the nature of dark matter. We have compelling evidence for its existence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background, indicating that it makes up approximately 27% of the universe's mass-energy content. However, we do not know what dark matter is. It does not interact with light or other electromagnetic radiation, which is why it is invisible. It also does not seem to interact strongly with ordinary matter. Despite decades of dedicated experiments searching for weakly interacting massive particles, or WIMPs, the leading candidate for dark matter, no definitive detection has been made. The identity of dark matter particles remains one of the most significant unsolved problems in particle physics and cosmology, representing a huge missing piece in our cosmic inventory. Equally perplexing is dark energy, which accounts for roughly 68% of the universe's total mass energy. Its existence was inferred from the accelerating expansion of the universe, discovered in 1998. Dark energy acts as a repulsive force, pushing galaxies apart, and its energy density does not dilute as the universe expands. The simplest explanation is that it is the cosmological constant, the intrinsic energy of empty space. However, theoretical calculations of this vacuum energy from quantum field theory predict a value that is an astonishing 120 orders of magnitude larger than what is observed. This cosmological constant problem is the largest discrepancy between theory and observation in all of science, indicating a profound misunderstanding of either quantum mechanics, gravity, or both. Its nature and origin are completely unknown, yet it dictates the ultimate fate of the universe. The unification of quantum mechanics and general relativity represents arguably the greatest challenge at the edge of knowledge. Quantum mechanics successfully describes the microscopic world of particles and forces, excluding gravity, while general relativity accurately describes gravity and the large-scale structure of the universe. Both theories are incredibly successful within their respective domains, but they are fundamentally incompatible. When one attempts to combine them, the calculations break down, leading to infinities. This means we lack a complete theory of quantum gravity, which is essential for understanding phenomena at extreme conditions, such as the very first moments of the Big Bang, the Planck epoch, or the interior of black holes. Theories like string theory and loop quantum gravity are ambitious attempts to bridge this gap, but they are still under development and lack definitive experimental verification. Beyond these major components, there are numerous other fundamental questions. The origin of the universe itself remains deeply mysterious. While the Big Bang theory describes the evolution of the universe from an extremely hot, dense state, it does not explain what caused that initial state or what existed before it. Was there a singularity? Did the universe emerge from a quantum fluctuation in a pre-existing multiverse? The very first moments before the Planck time are beyond our current theoretical grasp. Similarly, the matter-antimatter asymmetry, why our universe is overwhelmingly made of matter when equal amounts of matter and antimatter should have been created in the Big Bang, is an unsolved puzzle. The mechanisms that led to this tiny, crucial imbalance are not fully understood. The nature of consciousness is another profound mystery that bridges physics, biology, and philosophy. How does subjective experience arise from physical matter? Is consciousness merely an emergent property of complex neural networks? Or is there a deeper, more fundamental connection to the fabric of reality? While neuroscience continues to make strides in understanding brain function, the hard problem of consciousness, explaining why physical processes give rise to qualitative experience, remains elusive. Furthermore, the universe might contain phenomena or dimensions that are currently beyond our ability to detect or even conceive. The possibility of extra dimensions as proposed by string theory, or the idea that our universe is a holographic projection from a lower dimensional boundary, challenges our fundamental understanding of space and time. These concepts, while mathematically elegant, push the boundaries of empirical verification. The edge of knowledge is not a static line, it is a constantly shifting frontier. Each scientific breakthrough, while providing answers, often reveals new, deeper questions. The discovery of dark matter and dark energy, for instance, solved some cosmological puzzles but introduced even larger ones. This ongoing process of discovery and the recognition of what we do not know are essential drivers of scientific progress. The vastness of our ignorance underscores the incredible complexity and mystery of the universe, reminding us that its existence and our ability to ponder it are perhaps the greatest mysteries of all. For centuries, physicists have dreamed of discovering a single, overarching theoretical framework that could explain all the fundamental forces and particles in the universe. This ambitious quest is known as the search for a theory of everything, or TOE. The goal of a TOE is to unify general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, which describes the other three fundamental forces, electromagnetism, the strong nuclear force and the weak nuclear force, and the behaviour of matter at the microscopic level. Such a theory would provide a complete and consistent description of all physical phenomena, from the Big Bang to the present day, and from the smallest subatomic particles to the largest galaxy clusters. The history of physics has been marked by successful unifications. In the 17th century, Isaac Newton unified celestial mechanics, the motion of planets, with terrestrial mechanics, the motion of objects on Earth, under his universal law of gravitation. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, demonstrating that light itself is an electromagnetic wave. In the 20th century, the Standard Model of particle physics successfully unified the electromagnetic force with the weak nuclear force into the electroweak force, and it also describes the strong nuclear force. The Standard Model, confirmed by numerous experiments, including the discovery of the Higgs boson in 2012, is an incredibly successful theory, describing all known elementary particles and their interactions, except for gravity. However, gravity remains the outlier. Albert Einstein's general theory of relativity, which describes gravity as the curvature of space-time, is a classical theory. It works exceptionally well on large scales, explaining the orbits of planets, the bending of light by massive objects, and the expansion of the universe. But when attempts are made to incorporate gravity into the quantum mechanical framework, the mathematical calculations break down, leading to infinities and inconsistencies. This fundamental incompatibility between general relativity and quantum mechanics is the central obstacle in the search for a TOE. A theory of quantum gravity is needed to describe phenomena where both gravity and quantum effects are significant, such as in the extreme conditions of the very early universe, the Planck epoch, or within the singularity of a black hole. Several theoretical approaches are being pursued in the quest for a TOE. The most prominent and extensively studied candidate is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings, unimaginably small, roughly 10 to the power of minus 35 meters, the Planck length. Different vibration modes of these strings correspond to different fundamental particles and forces. A key feature of string theory is that it naturally incorporates gravity. One of the vibration modes of a string corresponds to the graviton, the hypothetical quantum particle that mediates the gravitational force. For string theory to be mathematically consistent, it requires the existence of more than the familiar 4 spacetime dimensions, 3 spatial and 1 temporal. Most versions of string theory require 10 spacetime dimensions, while its overarching framework, M-theory, requires 11 dimensions. The extra dimensions are thought to be compactified or curled up into incredibly tiny, unobservable spaces. String theory offers a compelling framework for unifying all 4 fundamental forces and all known particles within a single, consistent mathematical structure. However, it currently lacks direct experimental verification, as the energies required to probe the Planck scale are far beyond the capabilities of any foreseeable particle accelerator. Another leading candidate for quantum gravity is loop quantum gravity. Unlike string theory, which attempts to unify all forces, loop quantum gravity focuses specifically on quantizing gravity itself, without necessarily unifying it with the other forces initially. It proposes that space-time is not continuous but is granular, or quantized, at the Planck scale. In this theory, space is made up of discrete loops or networks, and time also flows in discrete steps. This approach attempts to construct a quantum theory of gravity directly from the principles of general relativity and quantum mechanics. While loop quantum gravity offers a consistent picture of quantum space-time and has made progress in understanding black hole entropy and the Big Bang singularity, it also faces challenges, particularly in fully recovering classical general relativity at large scales and in making testable predictions. Other approaches to quantum gravity include causal set theory, which posits that space-time is fundamentally discrete and that events are ordered by a causal relationship. Non-commutative geometry, which suggests that space-time coordinates do not commute at the Planck scale. And twistor theory, which attempts to reformulate physics in terms of fundamental geometric objects called twistors. Each of these theories offers a unique perspective on how to reconcile gravity with quantum mechanics, but none has yet achieved the status of a fully verified toe. The search for a toe is driven by the belief that the universe should ultimately be governed by a single, elegant, and consistent set of laws. Such a theory would not only provide a deeper understanding of the fundamental nature of reality, but could also offer insights into some of the most perplexing mysteries in cosmology, such as the origin of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. It would allow physicists to describe the universe from the very first moments of the Big Bang, where all forces were unified, to its present state, and potentially predict phenomena beyond our current observational capabilities. However, the path to a TOE is fraught with challenges. The extreme energies and incredibly small scales at which quantum gravitational effects become dominant make direct experimental verification exceedingly difficult. The mathematical complexity of these theories is also immense. Despite these hurdles, the pursuit of a TOE remains the ultimate goal for many physicists, representing the pinnacle of human scientific endeavour, a quest to find the single, unifying principle that explains why the universe exists and how it all works. The search for one continues, pushing the boundaries of human intellect and revealing the profound depths of cosmic mystery. The universe operates with remarkable regularity and predictability, governed by a set of fundamental principles that physicists refer to as the laws of nature. These laws, expressed most precisely through the language of mathematics, dictate how matter and energy behave, how forces interact, and how the cosmos evolves. From the smallest subatomic particles to the grandest galaxy clusters, these laws appear to be universal, applying consistently across vast distances and immense timescales. They are unchanging, meaning the laws that governed the early universe are the same laws that govern it today, and they are deterministic in many contexts, allowing scientists to make precise predictions about future events. Yet, despite our increasing understanding of what these laws are and how they work, a deeper, more profound question remains. What is the origin and fundamental nature of these physical laws themselves? Are they arbitrary, a mere cosmic happenstance, or is there a deeper reason for their specific form and existence? One perspective views the laws of nature as inherent, fundamental properties of reality. In this view, they are not imposed from outside the universe but are intrinsic to its very fabric, existing independently of any particular universe or observer. They are seen as necessary truths, perhaps even part of a larger, purely mathematical structure that simply is. This idea resonates with the unreasonable effectiveness of mathematics in describing the physical world, as noted by physicist Eugene Wigner. If the universe is fundamentally mathematical, then its laws are simply expressions of that underlying mathematical reality. This perspective suggests that the laws could not have been otherwise. They are the only possible consistent set of rules for a universe to exist. However, this raises the question of why these specific mathematical structures are realized, and why they are so perfectly conducive to complexity and life, a point that connects directly to the fine-tuning puzzle. Another viewpoint suggests that the laws of nature might be emergent properties, arising from a deeper, more fundamental level of reality. For instance, in some theories of quantum gravity, such as loop quantum gravity, or certain approaches within string theory, space-time itself is not a fundamental continuous background, but an emergent phenomenon built from more basic, discrete components. If space-time is emergent, then the laws of physics that operate within it might also be emergent, arising from the interactions of these more fundamental constituents. This would mean that the laws we observe are not truly fundamental, but are effective descriptions that apply at our particular scale of existence. This perspective offers a potential pathway to explain why the laws have their specific form. They are the macroscopic manifestation of simpler, underlying rules at the Planck scale, the smallest possible units of length and time. However, this merely pushes the question back a level. What are the laws governing these more fundamental constituents, and why do they exist? The concept of symmetries plays a crucial role in understanding the nature of physical laws. Many fundamental laws are deeply connected to symmetries in nature. For example, the conservation of energy is a consequence of the laws of physics being the same at all times, time translation symmetry. The conservation of momentum arises from the laws being the same at all locations in space, spatial translation symmetry. The conservation of angular momentum is linked to the laws being the same regardless of orientation, rotational symmetry. These symmetries are not just mathematical curiosities, they are profound statements about the universe's inherent order and consistency. But why does the universe possess these particular symmetries? Are they arbitrary choices, or are they somehow necessary for a consistent reality? The existence of these symmetries, which are beautifully described by group theory and mathematics, further blurs the line between a universe described by mathematics and a universe that is mathematics. The fine-tuning of the universe's constants, as discussed previously, adds another layer of complexity to the question of the nature of laws. If the laws are fixed and necessary, then their specific values, which appear so precisely calibrated for life, seem like an astonishing coincidence. If the laws are arbitrary, then their life-permitting values are an even greater coincidence. The multiverse hypothesis offers a potential resolution by suggesting that our universe is just one of many, each with different laws or different values for constants. In this scenario, the laws of our universe are not arbitrary in the grand scheme, but are simply one set among a vast ensemble. We observe these specific laws because only they permit our existence. However, this then raises the question of the meta-laws that govern the multiverse itself. What determines the distribution of laws across different universes? Are these meta-laws themselves arbitrary or necessary? The limits of scientific inquiry also come into play when pondering the nature of laws. Science excels at describing what the laws are and how they operate through observation, experimentation, and mathematical modelling. It can tell us that gravity follows an inverse square law, or that particles obey quantum mechanical rules. But science, by its very nature, is less equipped to answer the ultimate why questions. Why do these laws exist in the first place? Why are they the specific laws that they are? This question often pushes into the realm of metaphysics and philosophy, beyond the empirical reach of current scientific methods. Some physicists argue that the laws simply are, that they are brute facts of existence for which there is no deeper explanation. Others continue to search for a more fundamental principle, from which all laws could logically derive, perhaps a theory of everything that reveals a deeper, unavoidable necessity for the observed laws. The very concept of a law implies a regularity, a pattern that repeats. Without such regularities, the universe would be chaotic and unpredictable, making scientific understanding impossible. The fact that the universe adheres to these consistent mathematical rules allows for the emergence of order, complexity, and ultimately consciousness capable of discerning these very laws. Whether these laws are fundamental, emergent, or selected from a larger ensemble, their existence and specific form are central to the universe's ability to exist in its currently observed, life-permitting state. The ongoing quest to understand the nature of these laws is a testament to humanity's enduring curiosity about the deepest foundations of reality. The universe, while governed by precise and consistent physical laws, also exhibits an undeniable element of randomness or chance. This interplay between determinism, where future states are perfectly predictable from initial conditions, and indeterminism, where outcomes are inherently probabilistic, is a profound aspect of reality. Understanding how much of what we see is due to fixed laws versus unpredictable chance events is crucial for a complete picture of the cosmos and our place within it. In classical physics, particularly the mechanics developed by Isaac Newton in the 17th century, the universe was largely seen as a deterministic clockwork. If one knew the precise position and momentum of every particle in the universe at a given instant, and all the forces acting upon them, then the entire future evolution of the universe could, in principle, be perfectly predicted. This idea was famously encapsulated by Pierre-Simon Laplace in the early 19th century, who imagined a hypothetical demon with such immense knowledge and computational power that it could foresee every event past and future. In this classical view, chance was merely a reflection of our ignorance, a practical limitation on our ability to know all the necessary initial conditions. However, the advent of quantum mechanics in the early 20th century fundamentally challenged this classical deterministic worldview. At the microscopic level of atoms and subatomic particles, quantum mechanics introduces an inherent, irreducible randomness into the fabric of reality. This is not due to our lack of knowledge, but rather a fundamental property of nature itself. One of the cornerstones of quantum indeterminism is the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that there are certain pairs of properties of a quantum particle, such as its position and momentum, that cannot be known simultaneously with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This means that even if you knew everything possible about a particle at one moment, you could not perfectly predict its future trajectory, because its initial position and momentum cannot be simultaneously known with infinite precision. Furthermore, quantum mechanics describes particles existing in a superposition of multiple possible states until they are measured or observed. When a measurement is made, the wave function describing the particle's possibilities collapses into a single definite outcome. The specific outcome that occurs is fundamentally probabilistic. For example, a radioactive atom undergoes decay at a fundamentally random moment. While we can predict the half-life of a large sample of radioactive atoms, the time it takes for half of them to decay, we cannot predict when any single atom will decay. This is not because we lack information about the atom, but because the event itself is inherently random at the quantum level. This quantum randomness is a genuine, irreducible element of chance in the universe. While individual quantum events are fundamentally random, their effects often average out at macroscopic scales. The vast number of particles involved in everyday objects means that their collective behavior often appears deterministic. For example, while the decay of a single radioactive atom is random, the overall decay rate of a large sample of atoms is highly predictable. This is why classical physics works so well for macroscopic phenomena. However, there are instances where quantum randomness can have macroscopic consequences, particularly in highly sensitive systems. The role of chance is evident throughout cosmic evolution. The very seeds of large-scale structure in the universe, the tiny density fluctuations from which galaxies and galaxy clusters eventually grew, are believed to have originated from random quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. These random quantum events, amplified to macroscopic scales, determined where the first stars and galaxies would form, and thus the overall distribution of matter in the universe. On Earth, biological evolution is a prime example of the interplay between chance and law. Genetic mutations, which introduce new variations into a population, are largely random events at the molecular level, often caused by errors in deoxyribonucleic acid replication or exposure to radiation. These random mutations provide the raw material for natural selection to act upon. Environmental changes such as asteroid impacts, volcanic eruptions, or climate shifts can also be viewed as chance events that drastically alter the course of evolution, leading to mass extinctions or new adaptive opportunities. The laws of natural selection then provide the deterministic framework for which traits are favoured and how populations evolve over time. Without the element of random mutation, evolution would grind to a halt. Even in seemingly deterministic systems, chaos theory reveals how tiny, unpredictable variations in initial conditions can lead to vastly different outcomes over time. The butterfly effect, where a butterfly flapping its wings in Brazil could theoretically cause a tornado in Texas, illustrates how complex systems like weather patterns are inherently unpredictable in the long term, even if their underlying laws are deterministic. This is a form of practical unpredictability, distinct from the fundamental quantum randomness, but it highlights how chance can play a significant role in the unfolding of events. Ultimately, the universe appears to be a grand tapestry woven from threads of both fixed laws and unpredictable chance. The fundamental laws of physics provide the framework, the rules of the game, defining the possibilities and constraints for what can happen. They dictate how particles interact, how forces operate, and how space-time behaves. But within this framework, quantum randomness provides the inherent unpredictability at the most fundamental level, while chance events on larger scales introduce contingencies that shape the specific unfolding of cosmic and biological history. The universe is not a perfectly predictable machine, but a dynamic system where the interplay of law and chance leads to the rich, complex, and often surprising reality that we observe. The universe, at its most fundamental level, is described by a relatively small set of elementary particles and fundamental forces. Yet, from these simple building blocks and their interactions, an astonishing array of complex patterns, structures, and phenomena arise. This process, where intricate properties and behaviours emerge from the collective interactions of simpler components, is known as emergence. It is a concept that bridges different levels of scientific inquiry, explaining how the universe, despite its underlying simplicity at the deepest scales, can produce the incredible complexity we observe, from stars and galaxies to life and consciousness. Emergence means that the whole is greater than the sum of its parts. The properties of the complex system cannot be simply deduced by examining its individual components in isolation. A classic example of emergence comes from thermodynamics. The concepts of temperature, pressure, and entropy are not properties of individual atoms or molecules. A single atom does not have a temperature. However, when a vast number of atoms or molecules interact, their collective motion and collisions give rise to these macroscopic properties. Temperature, for instance, emerges from the average kinetic energy of the particles in a system. Pressure emerges from the force exerted by these particles colliding with the walls of a container. Entropy, a measure of disorder, emerges from the statistical arrangement of countless particles. The laws of thermodynamics, which describe how heat flows and how systems tend towards equilibrium, are emergent laws that arise from the underlying statistical mechanics of microscopic particles following simple rules of motion. In chemistry, the properties of molecules are emergent from the interactions of individual atoms. A water molecule composed of 2 hydrogen atoms and 1 oxygen atom has properties, like being a liquid at room temperature, its solvent capabilities, and its high specific heat capacity, that are entirely different from the properties of isolated hydrogen or oxygen atoms. These emergent properties arise from the specific electromagnetic bonds formed between the atoms and the resulting molecular structure. Furthermore, the self-assembly of complex biological molecules, such as proteins folding into intricate 3-dimensional shapes, or lipid molecules spontaneously forming cell membranes, are powerful examples of emergent order from simpler chemical rules. Perhaps the most profound example of emergent order is the emergence of life from non-living chemistry. Individual atoms and molecules are not alive. However, when vast numbers of specific molecules, such as deoxyribonucleic acid, proteins, lipids, and carbohydrates, interact in highly organized ways within a specific environment, they give rise to the emergent properties of life: metabolism, reproduction, self-organization, and evolution. A single cell, a marvel of emergent complexity, operates through intricate networks of chemical reactions and molecular machinery, none of which, in isolation, possesses the property of life. Life emerges from the collective dynamic organization of these non-living components. On a larger scale, consciousness is believed by many to be an emergent property of the incredibly complex network of neurons and their interactions in the brain. Individual neurons are simple biological cells that fire electrical signals. However, when billions of these neurons are interconnected in intricate ways, forming vast neural networks with trillions of synapses, the emergent phenomenon of subjective experience, thought, emotion, and self-awareness arises. We cannot find consciousness by looking at a single neuron. It emerges from the collective activity of the entire system. In cosmology, the large-scale structures of the universe are emergent. The universe began from an almost perfectly uniform hot, dense plasma. Over billions of years, gravity, acting on tiny initial density fluctuations, caused matter to clump together. This process led to the emergence of stars, which are highly ordered self-gravitating spheres of plasma. Stars then clustered into galaxies, which are vast rotating systems of billions of stars, gas, and dark matter. Galaxies in turn are organized into galaxy clusters and superclusters, forming a vast filamentary cosmic web. These hierarchical structures are emergent properties of the interplay between gravity, dark matter, and the expansion of the universe, arising from simple initial conditions and fundamental laws. The concept of emergence highlights that complexity does not necessarily require complex fundamental laws. Often, simple underlying rules, when applied repeatedly to a vast number of interacting components, can lead to surprisingly intricate and unpredictable patterns. Think of a cellular automaton like Conway's game of life, where simple rules for how cells turn on or off based on their neighbours lead to incredibly complex evolving patterns, including self-replicating structures. These systems demonstrate how local interactions can give rise to global order. Emergence is not a violation of the second law of thermodynamics, which states that total entropy tends to increase. While local pockets of order, like a living organism or a star, represent a decrease in entropy, this local decrease is always compensated by a much larger increase in entropy in the surrounding environment. For example, a star creates order by fusing light elements into heavier ones, but it radiates vast amounts of high entropy energy into space. A living organism maintains its internal order by consuming low entropy food and releasing high entropy waste products and heat. The universe as a whole continues its march towards increasing disorder, but within this overall trend, pockets of remarkable order and complexity can emerge and persist for long periods. The universe's capacity for emergent order is a key reason why it is not just a featureless expanse, but a dynamic, evolving cosmos filled with diverse phenomena. It explains how, from a relatively simple beginning, the universe has unfolded into the rich, structured, and conscious reality that we observe. The existence of emergent order is a testament to the power of fundamental laws to generate complexity, making the universe's very existence and its ability to produce such intricate patterns a profound and beautiful mystery.